if you're attempting to use the environment.yml file to set up an environment, a build issue on some platforms with some versions of CartoPy seems to have appeared in the time since we tested this. What I would encourage you to do is to download the environment.yml file from the tutorial resources and replace the one that exists in your current copy of the workshop. You could also just re-download the entire workshop if you want. We had to change it so that it explicitly specifies where we're getting CartoPy from. So you could also just edit your file locally and add CartoPy like it's the rest of the packages here under the dependencies section. That should work, hopefully. We're very sorry that it's this sort of inconsistent mismatch. We checked that it worked on Windows and on Mac OS X and on Linux, but in the time that that happened, it seems like there's some failures sporadically. So for those of you who do not have the environments configured yet, continue to just raise your hands as issues arise. There are also a binder environment for this workshop, which allows you to execute the code in the cloud. If you'd rather sort of do that than get concerned about setting up the environments, but I think it's always best for you to have your own local copy running so you can interact with the data. So I guess what we'll do first off is introduce, hello. This is the tutorial on intermediate methods for geospatial data analysis. Welcome. This is the second in a series of workshops that we gave last year on an introduction to geographic data analysis. And that dealt with sort of the primitives of geographical information, so how you represent things like points, lines, and polygons in geographic information systems in Python, and then how to do some sort of basic querying and manipulation of that data, all the way up to some more advanced topics on statistical explorations and the analysis of spatial structure and data. My name is Levi Wolf. I'm a lecturer at the University of Bristol in the United Kingdom. And this is...
I'm Serge Ray. I'm professor at UC Riverside. I run the Center for Geospatial Sciences there, and I'm co-chair of the meeting this year. So thank you all for coming. We're going to tag team today. Levi is going to deal with the first half up to the break, and then we'll swap, and I'll take over. So that means I can range around and help people in the first half. If you have a question or get stuck on something, raise your hand, and I'll come around and try and help you out. And then Levi will do that in the second half.
Cool. The format of the workshop is broadly organized according to the schedule that's listed in the README, in the tutorial materials. There will be problem sets for each collection of notebook. So we're going to start off working on a notebook on spatial relationships. And this is about sort of classic concerns in GIS about who's nearest to me, what spatial joins relate different geographical objects together. And then there's going to be a problem set where you'll take the stuff that we've walked through and then apply it on some new data to try and answer some questions about the structure of 311 cases reported in Austin. So broadly speaking, it'll be sort of a presentation on a notebook, which you all should walk through as we're doing it, and then a problem set where you get about 20 minutes or so to try and solve the problems using techniques that we talked about throughout the tutorial. Before we proceed, raise your hand if you're still having environment issues. A couple, but quite a few. Okay. Does anyone else have any issues generically about the content of the tutorial or about what we're going to do before we get started? Awesome. Okay. If you are still having environment issues, can you keep your hand raised so that Serge can come around and check on some of the statuses? And then I will proceed to the first set of content. So Are all of you aware of how to open Jupyter Notebooks in either a Jupyter Lab or a Jupyter Notebook viewer so that you can walk through the tutorial? Normally that would involve opening up Anaconda Navigator, getting to where the files are located on your hard drive, and then opening the file. We're going to start off with the first notebook called GDS1-relations.ipynb. Okay? So, geographic data comes in a lot of different representations and conceptual structures. In this notebook, we're mainly going to be talking about the structures and relationships between what's called vector data. And vector data usually comes in 3 different kinds of flavors. Points, which conceptually represent a specific single location in geography. Lines, which represent some collection of continuous space one-dimensionally along a particular path. Usually those are composed of individual straight line segments in the GIS. And then finally, we're going to be talking a little bit about polygons, which are patches which usually have lines defining their boundaries or internal holes. We're going to be talking a little bit about how to do some pretty plotting of this data in a little bit more advanced of a way than you learn typically with standard GeoPandas tools. And then we're also going to talk a little bit about geocoding, which is the process of constructing geographic data from textual data, and then also constructing textual data from geographic data. And then we're also going to talk a little bit about zonation, which is one way that you can conduct sort of a spatial group by of points. And then we're going to talk about classical sort of ideas behind spatial joins, spatial queries, and in particular spatial nearest neighbor queries. So the first thing that we'll do is we'll be introducing in this notebook about 4 or 5 libraries. But the central ones for most of this workshop is the GeoPandas library. And this is incredibly small. Cool. Setting single document mode. Cool. So we'll be using these 3 libraries, GeoPandas, Matplotlib, and Pandas, pretty extensively throughout the entire workshop. In this notebook specifically, we'll also cover a little bit of the Contextually library, which is a library responsible for generating map base tiles, the GeoPy library, which deals with geocoding and reverse geocoding data, and then we'll also talk a little bit about the SciPy library's spatial submodule, and in particular, some of the things that you can do using SciPy Spatial. So first off, geographic data comes in a large variety of formats. And oftentimes, when you're working with people who don't do GIS work on a day-to-day basis, you're going to have to learn how to parse geographic data by hand. One of the more common ways that people export geographic data, especially for points data, is just in terms of a flat text file. So here we've read in 2 data files that we're using today. They're compressed, comma-separated value files. And this is actually usually a little bit nicer than what people will give you. They'll usually just give you raw CSVs, which tend to be wasteful and somewhat dirty. Here, this is a set of data on neighborhoods in Austin, Texas, that's in a CSV, and then a set of Airbnb listings that have been scraped from Airbnb, containing information about their price or their amenities or sort of different descriptions that the host has written about the property. And when we look at this listings data, we can see that most of it is textual. There's 5 rows and 107 columns, and at some point, we see a geometry column. But in general, we see that there's a ton of information about spatial context. We get some columns that refer to the city. We get some columns that refer to the state. So let's see here. City, we get state, We get some information about the zip code. We actually get this internal variable called market, which is the area that Airbnb thinks that this particular listing competes in. You get some information about latitude and longitude, which is the actual point location of the listing. And then you also get some other information at the end here called geometry. And this is because it's a database export. It comes out in well-known text. In the neighborhoods data, we have polygon information. So these are going to be a collection of polygons that represent the area of every single neighborhood in Austin, Texas. And these polygons only have 3 bits of information with them, 3 columns. You've got a hood ID, which is kind of like the neighborhood identification number. You have an information about the group that the neighborhood falls in, if any. And then we have this column called WKB. WKB is a very common format for exporting geographic or geometric information from spatial databases, and it stands for well-known binary text. Well-known binary text comes usually in 2 different flavors. This looks like a large string. Let's see. This looks like a large string where the very first part of it is providing some information about what type of shape that shape is. And then the rest of it, basically everything that comes after this AC, is encoding the coordinates of that polygon in a textual representation. Okay, so this well-known binary is a common format used inside of databases like PostGIS. If you use SQLite, the Spatialite extension will also use this kind of export by default. So this is a very common mode of geographic data, but it's not really that clean, right? You're probably used to hearing more about things like GeoJSON or shapefiles or geopackages. And those are much cleaner data. You can usually just use geographic information systems to read that in, like we did in pandas, using the geopandas.read file. We'll do that later. Instead, to create geometries, you'll have to learn about the different constructors that take textual data and process it into shape data. So one of the ones that was added to GeoPandas quite recently is this points from XY functionality. And points from XY parses latitude and longitude information. In this case, it's actually stored as X and Y, so it's longitude then latitude, and turns it into a geometric representation in Python. So when you run points from XY on XY coordinates, here we're sending it the listings longitude and the listings latitude, it turns that information into a list of points. Now, this is an intermediate workshop in geographic data science, so we won't cover geographic analysis, so we won't necessarily cover a lot of Shapely, but Shapely in Python is a library that is that provides the geographic primitives for geographic data. So when we mentioned before that geographic data usually comes in 3 flavors, geographic vector data, points, lines, and polygons, Shapely is the package that defines all of those classes and their structures and their relationships. If you're interested in learning more about these kinds of very basic geographic primitives for how to represent geographic data, last year's workshop on beginning intro to geographic data analysis provides a really thorough overview of those geographic primitives. Now we're going to sort of skip that thorough intro on geographic primitives and move to sort of using them to make geographic information science happen. Okay? So we're not going to spend a lot of time dealing with the actual underlying mechanics of the Shapely library. But that's what happens when you use points from XY. Points from XY takes textual representations of data or float representations of data just in coordinates and then turns it into this proper representation in Shapely. So To build a geodata frame, there's a lot of different ways you can do it. And the GeoPandas geodata frame constructor takes the most common way to work with this constructor is to send some kind of data frame-like object and then tell GeoPandas where you expect the geometric information that corresponds with each row to live. So here, we're sending this listings data frame, not had, sorry, head, not headed. We're sending this listings data frame, which has a bunch of columns and a bunch of ways that the geographic information is represented, but we've just built up this collection of geometries inside of geometry down here, right? So we called geopandas.points from xy to take the raw longitude and latitude coordinates and turn them into shapely representations. And then we're telling GeoPandas this list of shapely objects corresponds with every single row of that original listings data frame. So we build the geometries, and then we send something that looks like a data frame and some information about the geometries down to the constructor. Now, there's a lot of different ways that this constructor can work. If you have a shapely object stored in every single row of your GeoPandas data frame, you can give this a string. And then the GeoPandas constructor says, okay, I know where to look for the geometry, and I'll construct a geodata frame just fine. So now, I've got a geodata frame where at the end here, I have this column full of geometries that are the correctly processed versions of our original latitude and longitude. But if I look at the very first one, it's still a shapely point. It's getting transformed here because of the representation in the IPython notebook. But this is no longer a float or a string. It is a shapely point. So GeoPandas needs to know about your data frame-like object, and then it needs to know about where the geometry lives. The geometry could live in something else, like a list of shapely objects. It could live inside of the GeoPandas data frame and sit in a column. They just need to be aligned. So the GeoPandas constructor sort of zips them up together and makes a distinct object called a geodata frame. Okay? This is kind of special because, like in pandas, you're usually got all these different from whatever accessors that allow you to take a bunch of different data structures and turn them into a pandas data frame. This strategy for GeoPandas means that you can take basically anything that you can turn into a pandas data frame and then just shove in that geometry column later and turn it into a geo data frame. So all of the constructors from pandas still work and give you pandas data frames, but once you need to do spatial analysis, you can then convert them into a GeoPandas data frame and use that. So for x and y, we can use this handy helper function, geopandas.fromxy, or geometry from xy. But for parsing well-known binary, or an equivalent representation known as well-known text, which is that whenever you see something like, whenever you see this kind of point and then this text here, this is what well-known text looks like. The Shapely library has parsers for these various kinds of geographic representations. So you don't need to worry about writing a representation or writing a parser for well-known binary or for well-known text. If you import the module from Shapely, then you can use the well-known binary.load string shape, and in this case, the well-known binary is in a hexadecimal encoding. If the well-known binary wasn't in this encoding, I'll show you what that looks like in a second. But it's standard, typically in geographic databases, to export well-known binary in a hexadecimal encoding rather than in a raw encoding. So here, when we're using this well-known binary column, remember this is neighborhoods. This is the data frame that looks like this with 3 columns, one of them with a hood ID, and at the end here we have this well-known binary string, which is really long. We're going to take each row and we're going to parse that information into a usable data. So that's the first well-known binary string. And if we use the Shapely well-known binary dot loads, hex equals true, we parse that into a shape. And if we want to do that for every single row of a pandas series, we can use the apply method of that series. So here, we're using a lambda, which is like an anonymous function, but that may be too. So if I wanted to say parse geometries, and you get a well-known binary string, you would return wkb.loads, well-known binary string, hex is true. So if we wanted to parse this, you would do the same thing we did above on each string by applying parse geometries. Now, every single row is a polygon. It is a Shapely polygon. It's been turned from this large string representation into the correct object representation. So like that's what the first neighborhood in the data frame is. That's what the second neighborhood in the data frame is, and so on. But even though we've converted all of these things into Shapely objects, we haven't actually solved the problem of making a geodata frame. Like before, I was talking about the GeoPandas geodata frame constructor. And the GeoPandas geodata frame constructor needs to know where your data frame-like object is, and then a collection of geometries which you can use to create a geodata frame. So here, our neighborhoods data frame, oh shoot, sorry, I ran the cell ahead too quickly. Let me go back and repopulate it. Cool, sorry about that. So the neighborhoods data frame, again, which looks like this, where you have that well-known binary, and then we parse it. After we parse it, we get another column called geometry that has that textual representation, right? It's still not actually a GeoPandas data frame. It's still a standard pandas data frame. So in order for us to use it for spatial computations, we have to use the geopandas.geodataFrame constructor. Now this, no, that's not what I want. I want that. So this constructor implicitly assumes that your geometry is stored in a column called geometry. So that's the default, is if you give a geodata or a data frame-like object to the GeoPandas data frame constructor, it's going to look in a column called geometry to try and see if you've stored a geometric object in your data frame already. So just by default, this looks in that geometry column and grabs the correct type, grabs the correct geometry, and then now we've converted that into a geodata frame. Yeah?
So I was just tinkering around in there, and I saw that listings had a function called setGeometry on there.
Yep.
And it seemed to simultaneously set the geometry and convert it to a geodata frame at the same time.
Set geometry only exists if listings is a geodata frame.
Right, I thought that, but I converted it. It was written in a data frame, and then I saw that it had the set geometry property on there.
If so, that's very new. What? I don't think that's the case, is it?
Listings.set
Whoa. That must be in the, oh, that means that, so recently there was an update to GeoPandas that takes account of this refactor that I think was released in the last week. So if that's the case, it must be because importing GeoPandas monkey patches the original class. So if this is true, then this is really new. Good call. I didn't think that this had been released yet. Oh, 5.0, yeah. Yeah, so that is possible. If you do have this set geometry column, set geometry now will monkey patch into the original data frame. And set geometry, we'll talk about a little bit later, also allows you to switch between geometric representations inside of a single data frame. So if you want to talk about, if you have like, say, I don't know, a polygon with two different representations, or a point that has a buffer around it that you computed, which is like an area which you're going to search inside of, you can use set geometry to switch between those representations. And recently, set geometry, I guess, also has been patched to process geographic information inside of columns and cast it directly into shapely objects at the start. So that's interesting that that's there. I wonder if that's actually processing the text, the plain text on the geometry column. Anyway.
I just passed in the GeoPandas that point to the next slide in the set geometry. And it just
Yeah, I think that that's another. Set geometries works by looking at any column or any other constructor, just like the original geodata frame constructor. So, but that's interesting. I think that that's just merged in 5.0, because that was a request that I made. That's cool. I'm glad that they put it in. So anyway, when we're building the geodata frame stuff for the neighborhoods, by default, it looks inside of the column called geometry. But you could call your geometry column anything you want. In GeoPandas, this can be kind of confusing. And if you look at some issues for GeoPandas, you'll see lots of people ask this question. The difference between, so once you have a geodata frame, the difference between the geometry column, which is a specific column in the data frame called geometry, and the actual geometry attribute, which is what the data frame has as considered as its active geometry column, those two things are different. So if you would have called your parser up here when we parse this WKB, if you would have called it something else like parsed geometry, you can construct a data frame still and have that column still be called parsed geometry. Some database installations I've seen have geometry columns called the geom. And if that's the case, then you just send the geometry column that you expect, and GeoPandas will parse that into a geometry. But by nature, if you use the dot geometry attribute, that will always look for a series inside of your data frame, which may not necessarily be named geometry. So to show you what I'm talking about here, you can use dot rename. Let's say geometry equals new geom. So now this geometry column actually has a different name, but dot geometry can't find it because it's looking for the column that happened previously. So set geometry will make the geometry column refer back to the name that we used earlier. If we have this, let's say different name, then the geopandas.geodataFrame constructor on different name would have to say geometry equals new geom in order to get a data frame back. So this kind of division between the column called geometry and what GeoPandas actually records as the geometry column You have to keep those two concepts distinct. For most cases, if your column is called geometry that you want to work with, you're fine. But sometimes people will encounter these problems where they're using set geometry or reset geometry or renaming columns where this happens, and you will get into trouble if you don't see the difference between those two methods frequently. So just as a side, since we were talking about this, the set geometry stuff, you want to be sort of careful about what you're calling these geometry columns. The default name is geometry. Most operations will work correctly if you use the default name. Should be fine. Writing out to file is done using a to-file method on each GeoPandas data frame. Setting coordinate systems, though, is rather important when you're working with geographic data. Coordinate reference systems are sort of geodetic conventions that allow you to agree on accuracy or representations of geographic data. So when you're working with coordinate reference systems in GeoPandas, this is conducted through the .crs argument, or the attribute. And this is another thing that is standing to change here on a new release of GeoPandas. But right now, the proper convention for working with coordinate reference systems tends to be specifying a correct proj4 string in this manner. Since we've parsed the data from latitude and longitude, in both cases, we're going to set its default or its initial coordinate reference system in this manner. When you have data that comes from plain text and has no coordinate reference system information, you set its coordinate reference using a dictionary where the key is init and the value is something that kind of looks like itself a key value pair of what referring authority you're using and then the code for that projection. This could also be a proj4 string. That should be fully supported as well. So here we're going to be setting coordinate reference systems on our data frames, and then I'm going to be writing these out to geopackages for later use. So that's kind of the higher level working with GeoPandas data frames, constructing them from plain text and working with coordinate referencing systems, initializing them when you don't have them. Okay? The second part, writing the listings will take a while because the format, geopackages, takes a bit. Are there any questions just on this basic construction of the data frames and working with geometric columns? The difference between the column named geometry and the actual geometry attribute? Anything? Yeah?
I mean, just like pandas, if we wanted to add Nordic and Easting as like another set of coordinate system, it's just the same way of inserting another column and then calling that into it, right?
Yep. Yeah. So you can always add an arbitrary number of columns, and you can switch between them using that set geometry operation. So if you wanted to have both a projected and an unprojected thing inside of a data frame, you could do that. The standard way to do that would actually be, and we'll do this in a second, listings.toCRS, and then you cast it when you need it. But if you have large data frames or the reprojection is difficult computationally, then you might want to store the pre-computed points. But yeah, you can method chain on a lot of these different things. So like the toCRS attribute will reproject your data, and then you can use a method on top of that to plot it. We'll do that in a second. I can show you. But yeah, you can always store arbitrary numbers of columns and then use set geometry to recover. Are there any other questions on geometries and construction before we move on? Yeah?
For setting CRS, can you talk a little bit about when you will use key value pair and like that's true? Or?
I'm pretty sure it assumes that by default, but I'm not sure. When you'd use it is, more often than not, if you're coming from a context where you're parsing data from plain text, you'll need to get the exact information about what's going on in the coordinate reference system. Here, I'm just using this EPSG code because it's simpler and concise for the example. But if you know more about the context of whatever data you're reading it in, you need to use that information on that.
I would recommend just using .f equals true.
Yeah?
Whenever possible.
Sure.
If someone asks a question, could you repeat the question because they can't pick it up?
Got it. Yeah. So the question was when should you use nodef equal true or additional sort of default options on or additional options on the proj4 information? Yeah, it's whenever possible. If yeah.
Yeah, it's actually the option to do no defs was removed in Proj 6.0.
Okay. So I tend to just use the EPSG codes and get away fine. I think for geodetic operations with high precision, you've got to be more careful about parsing stuff from plain text anyway if it's uninitialized. But yeah, I think in general, GeoPandas will recognize coordinate reference systems when read to file. So if you have a projection that you want to use, then it should be fine. Any other questions?
So
Yeah.
what is the GPKG file have?
The GeoPackage file is a spatial data format which stores all of the sort of attribute data, the columns that aren't geometric, in addition to the geometries together. My understanding is it's implemented inside of like a SQLite database. You don't need to really know a lot about how that operates. But it's just like another geographic data format. There are quite a few drivers that are available in GeoPandas. These are all coming from another library called Fiona, which is responsible for managing geographic information, writing and reading of vector data in Python. But GeoPandas just sort of sends that all to Fiona. Any other questions? Cool. So this next part's relatively straightforward. We're going to be working, I'm going to show you how to do geocoding. Raise your hand if you've heard of geocoding before. Okay, quite a few of you. Have you ever used GeoPy before? Some. Okay, so GeoPy is sort of the standard library to do this in Python. I'm showing you how to use the Nominatum API, which is a OpenStreetMap geocoding API. But GeoPy has access to many, many, many different types of geocoding endpoints. So if you have one or your organization has one that you find to be easier to use, you could always follow that and use that here. So GeoPy works by sort of instantiating a coder object, which then processes all of the queries that go through the API, the Nominatum API. So here, we're actually initializing that geocoder object. And that geocoder object has a bunch of different ways that we can work with the API to geocode information. The first one is the actual URL, which the API is exposed at. So if you have that, you could always go to it. And this is the geocoder endpoint that we're actually going to be using. Okay? So today, I'm just showing you how to use Nominatum from the GeoPy package. But there's a bunch of other ones. You could use the ArcGIS one. I think there's one for the, is it, yeah, so there are quite a few different endpoints that are available. So when you're working with geocoding, geocoding can go sort of in two directions. I'm going to show you how to do both here. But geocoding, when you say, I'm going to geocode some information, it tends to be operating from an address and then giving you a location. So geocoding, when you classically think of it, is going to be an address that gives you a particular coordinate in space. Reverse geocoding looks up addresses given coordinate values. So in our Airbnb data, we have a bunch of coordinates, right? We have a bunch of longitude and latitude values, and we might want to know the address or the closest address at which each of those listings is made. So if we do that, we would be reverse geocoding. We're reverse geocoding because we're going from the actual coordinates into textual data. So here, there's a bunch of options on how to conduct that query, but the main point here is the coordinates you wish to obtain for the closest human readable addresses is the very first option. So that needs to be a pair in terms of latitude and longitude. That gets coded. Note that this is YX order, not XY order. And then we code that point for that Airbnb listing into the closest address. And this is done by taking those coordinates, sending them to the OpenStreetMap Nominatum service, and then pulling back down some representation in text. So this very first listing in our data frame says that it's 314 West 37th Street, right? Now, this also gives you information about the raw content of that request. that raw content here can give you additional information, things like the bounding box on where the service thinks the address is. It can give you some information on sort of the neighborhood, OpenStreetMap neighborhood where the point lies. So if you ever want to access like the raw contents of any of the APIs, you use the raw attribute, but nominating here provides this amount of information. And since what we want to do is we want to do this for every single row, maybe, to get a textual representation of where our Airbnbs are, we can do the same trick that we saw before and define that operation using an apply method. Now in pandas, when you apply a function to a data frame, it ends up operating column-wise. And what we want to do is we want to take the latitude and the longitude of each row and send that to our query. So kind of like how NumPy works, we have to use the axis argument to make sure that we operate over the pairs inside of each row rather than operating down each column. So here what's happening is we're getting that reverse geocoding of each coordinate, grabbing the address, and making sure that that's operating on each row the XY coordinates. So when you run that, it makes these 20 web requests using the default settings of the geocoder, and then we'll return back a list of addresses that correspond with those coordinates. And we get a timeout because probably the internet in this space isn't too nice, service timed out. But in general, if we were on better internet, this would run fine and return all of the textual representations just like this original one here. We would get the full address string of that request. Now, when we're working backwards, you use the we've been working backwards. When you want to turn an address string into a location, you just use the geocode method. So if I wanted to geocode a coordinate, or geocode the actual location, the actual textual representation of the location, then using geocode, you'll get the same kind of object back from GeoPy. So if you use reverse, you get a location where the textual representation corresponds to the point. And if you use geocode, you send the textual representation, and at the end of that, you get back your latitude and longitude, here 30 and 97. Okay? So working with the GeoPy will let you do this kind of conversion from latitude and longitude into addresses or from addresses back into latitude and longitude using these geocode and reverse geocode methods. Of course, you want to be careful because there's a ton of conditions on how to use this that you have to be careful about in order to ensure proper usage. So what I would encourage you to do maybe is to play around with some of the coordinates in the data frame and maybe try a couple of requests yourself. So see if you can't generate a couple of correct geocodings from the coordinates in the listings data frame. So you would want to use reverse to get back the address, and then try geocoding that address again to get back to the latitude and longitude. So let's do this for about 5-6 minutes or so, see everyone get sort of like a functional use of some of these coordinates. And we'll walk around asking any questions. But this is just like 5 minutes or so to get your head around using these geocoding options. And if the internet doesn't work, let me know, and then we'll we'll move on because everyone's getting timeouts. So go ahead. Here we're going to be doing some cleaning of the data. This price data, again, comes as plain textual information. So the prices are listed in terms of how they would look on a website with a currency indicator, and then commas separating the thousands. So what we need to do is we need to parse that into a different representation of the string, which looks with underscores, has no additional methods, no additional information other than things that Python can understand. So here, there's a lot of different ways you can do this kind of string substitution. What I'm showing you here is one that separates them out into individual operations, so you can understand at each step what is being substituted inside of the string. So what we want to do is we want to take each price and we want to remove that dollar sign. And so here I'm just suggesting that we replace any instance of a dollar sign with an empty string which says drop any dollar sign in the price. You could do this by using an rstrip command or an lstrip command, which would pick that only parts that start with or end with. There's a lot of different ways to do this. The .stir operator, I should be sure to mention, make sure that pandas applies string methods to every cell that you're talking about. So here, I'm able to use this .replace, and this .replace is referring to a replace on the string. It's not referring to a replace operation in pandas, which would take a cell value and replace it with another cell value. So here we're going to be using the string methods to swap out dollar signs, commas, and things like that for stuff we can parse. So first we're going to be swapping out our dollars. Then we're going to be swapping our commas into the separator, the thousand separator that Python can understand. This is, some people haven't heard or seen this representation before, but in Python you can use underscores in the middle of numbers as thousand separators to give them sort of visual chunking. Any listing that doesn't have a price, that has no price information on it, it's just an empty string, should get replaced with the correct missing data indicator. So here we're going to replace that with a NaN value. And then we're going to convert that price into a float. So each of these things is operating in sequence. We're going to swap out those dollar signs. We're going to swap out those commas. We're going to replace the missing values. And then we're going to convert them into a float. So now we've turned our data, which looks like string representations of prices, into numeric data that we can work with. So we're kind of moving all the way from flat text information down into data that we could do some analytics on. So now that we've done that, we can make sort of these histograms of nightly prices in Austin. And if you look from this scraping, there's one listing that has a nightly price around $10,000. An Airbnb, $10,000 a night.
That's where I'm staying.
So one of the nice things about this data is that you can actually use the listing URL to look back up what that scrape corresponds to. So here, in our data, we see that it's the Arrive Sapphire on Lake Austin is the most expensive listing. And so when you actually look at that listing, if the web will be, this is what you get. So $9,000 a night, 12 beds, very nice space, right? So our data includes everything from things that are very cheap all the way up to this. So for most analytical purposes, we kind of don't want to deal with these extreme outliers. We want to deal with sort of the majority of the data. You can use outlier robust methods. Here, and for some of the later analytics, we're just going to say we're kind of categorically not interested in the Arrive Sapphire. And to filter in this manner, you can use the quantile functions in pandas to split up your data. So here, we're just taking the middle 98% of the data. We're dropping off the top 1% and the lower 1% of prices. And when you do this, you still get a pretty unequal distribution of prices. Oh, that's unintentional zooming there. You still get a pretty variegated distribution of prices, but none of them are quite like the Arrive Sapphire. Okay, so we're just filtering it in to sort of give focus onto, but you could use outlier robust analytics, and don't worry about this. I'm just doing this here for the purposes of the workshop. Now we get to using base maps. Base mapping is useful because we want to be able to make pretty maps. And in Python, there's a really sort of newcomer library that's effective for making basic matplotlib maps that have geographically correct base map information with them. That library is called Contextually. Contextually looks at web services that provide tiles. These are sometimes called tile servers. They grab the tiles from the tile server and allow you to stick them underneath your map like an image. So what we're showing you here is how to do this kind of underlying or underlaying of images on vector data from GeoPandas for any kind of image. You could have your own images that you want to over or underlay. But here we're just going to be talking mainly about base mapping through Contextually. The first thing that I'm going to recommend that we do, because we're using web tiles, is to convert our data into Web Mercator projection. And doing this will let us sort of talk directly to the web tiles. Learning how to do the reprojection of the actual web tiles and all the rest of that would be sort of an additional collection of topics where we're talking about reprojecting raster data. And we're not going to hit that just yet. So first off, we're going to be reprojecting this into Web Mercator. And what this does is provides us with an alternative representation. So before we had our latitude and longitude, and when we use the 2CRS, it takes the data. So let's say it takes the data and converts every listing into a new listing where we get new coordinates. So you can use this in a way that allows you to method chain. So if you wanted to just convert the data into a coordinate reference system to do one operation, you can always access that on that underlying data frame. But here we're just going to keep around the Web Mercator projection for doing some mapping. So when you make this array, the GeoPandas attribute has this total bounds attribute. And the total bounds is basically the bounding box of what's in that geodata frame. And the nice thing about this is that it's computed on the fly. So if I subset my data or change what observations I'm looking at, then this total bounds will look only at the data that I'm talking about and get the maximum extent from that data. So this means that you can use total bounds to sort of get a rough indicator of the bounding box of all the data that's inside of your geodata frame at the time. Contextually, as a library, takes that bounding box and grabs all of the web tiles that intersect with it, clip them together into a single image, and returns that image and its apparent geographic extent. To do that, you have to specify those coordinates, those west, south, north, and east corners, and then you have to specify a zoom level. So for those of you that worked with web mapping before, the zoom level is kind of like how much detail on the base map there is and how sort of tightly it should be displayed. So here what we're doing is we're using something called splatting or unpacking to take that total bounds information and convert it into the format that Contextually expects, which is each individual coordinate rather than a list of coordinates. And we're telling it to grab a zoom level of 10. Anytime you have an iterable, you can use that star to say, okay, what I want you to do is I want you to look inside of that iterable for each element. Right? So this is kind of like a nice way that you can work with ordered data in Python, is using these kinds of unpacking operations. So using Contextually, making this web request, we get two objects, always two objects that are returned. You get the base map, and you get that base map's extent. So here you see this base map, and that isn't a very pretty base map. Indeed, it's actually a NumPy array. The NumPy array is multidimensional. It contains a standard RGB kind of band, and then has the extent showing you where each pixel is. And then the extent is just another iterable, but that extent contains the corners of the image. Now this is kind of confusing sometimes, because this extent is in a different order than the extent that we sent contextually. And this is because in geographic analysis, it's common to give coordinates in terms of two corners. And in Matplotlib, it's common to give coordinates in terms of left, right, bottom, top, or top, bottom. I can't quite remember off the top of my head. I think it's top, bottom, top. But the point is, basically, you've got one format that's interleaved, x values and y values, and another format that's x min, x max, y min, y max. So just so you know, there's going to be a lot of that kind of conversion between the two when you're trying to work between geographic data in raster format and Matplotlib. But using plotting in GeoPandas, there's a lot of different tutorials on this. But one of the nice things about GeoPandas is that this plot method is built in and allows you to do some really simple choropleth mapping, right? So if I have spatial data and I want to make a map, I can just say, give me the geographic representation of that data. Now, that works for points and it works for polygons, it works for anything, right? So it'll take that data, it'll give you a plot of that data just fine. You can make very simple choropleths, because by default, it'll allow you to do that color and styling. So here what we're doing is actually making a composite plot. And stepping through it line by line, we're making a figure that's big enough to contain the axis. And then in that figure, we're plotting the boundary of neighborhoods. So what is neighborhoods.boundary? Well, every GeoPandas data frame has a bunch of different kinds of methods of accessing things about its geometry. And neighborhoods.boundary allows you to get the line that encloses the polygon. So using geopandas.boundary, you can start talking about spatial relationships that involve just the boundary points of those polygons. So here I'm using neighborhoodsboundary.plot and want to color them orange-red. And then I'm putting the listings inside of those in small points and calling them green. So when you run that plotting call, you get this kind of figure. Just as an aside, you can also focus on the boundary of shapes by doing face color equals none, and I think it's edge color equals orange red. But I prefer thinking about the boundary solution because it gives you more of a sense of exactly what's happening, right? You want to take the boundaries off of the polygons and then you want to give me those boundaries instead of sort of thinking about how matplotlib thinks about parameters of plotting patches. If it's easier for you to think of face color equals none, do that. So you can make these composite maps using multiple different geodata frames in the same coordinate reference system. To add images, you use the imshow command, which sticks that image always below other stuff that you're going to plot on top of it. So here, we've gotten the base map from Contextually. We've gotten its extent. I'm using interpolation here so it looks a little prettier than normal. And then we're doing the same call from above. We want orange boundaries and green listings. But at the very first part, we're using imshow to stick the base map below. Right? We got the base map from Contextually. And now you've got that spatial information here in a map with a pretty base map. So yeah, that's kind of base mapping on the basics. You're using imshow to provide the base map. You're using the boundary.plot there to send the boundary information, and you can do this for any arbitrary number of things you want to plot. Using further stuff in Contextually, you can grab a bunch of different kinds of maps, base maps. So Contextually by default has in contextually.tile providers, it has a bunch of OpenStreetMap providers. It has a bunch of Stamen providers. That's just what's built in. All of these are URLs that you can use in the contextually bounds to IMG function to grab different base maps. So here I'm grabbing the Stamen toner base map and making a map in the same way as before, but using a different image for my base map. Right? So there's a bunch of different ones that are made available. You can also use an arbitrary URL. So if you know of a tile server that you like, I used to use Carto tiles. The positron tile is really good for some digital cartography. If you want to use a tile for yourself, it has to be formatted in this format. It's slightly different than some of the standard ways, like if you go to the OpenStreetMap tile server listing, slightly different format. But then if you pass that to the URL, it queries that server for tiles, and then you can make a map with those base maps. So that allows you to do it. I have a stub for using GeoPy and Contextually to make a map of your hometown. But we're going to be running out of time if we continue at this pace. So what I'd rather do is move to the last sort of, well, actually, no, we'll take this. So in the next sort of 5 to 10 minutes, try geocoding an area that you know, using the bounding box from that location to get a web tile, and then try and use that web tile to make a map. Just show that web tile. Okay, so that might look like something like coder dot, let's say geocode, I don't know, 800 market. And then with that latitude and longitude, contextually dot bounds to image. And you'd want to say, give me the area around that. So let's say, give a little bit to the left and right. And then use plt.imshow to show the map. Okay? So for the next 5 or 10 minutes, try and piece together those three. You might have to use the lat long equals true argument contextually. But just try and use that to make a basic image of some location that you know about. Okay? For the next 5, 10 minutes. Like before, raise your hand if you have questions on how to string these three together. To move on, it's all right if you didn't get this immediately. There will be part in the exercise where you'll be building some things from data as well. So there's a part on this notebook talking about building up areas for regionalization or for visualization. And in this case, this is relatively, we're building up a boundary over a bunch of different spatial operations. I think it actually might make sense to take a break in about 5 minutes, or just say take a break now, regroup here at 3, and then we'll go through the last bit of this notebook and then do the problem set rather than what I said before. So I think it might make sense to take the break now because this is before we pivot into sort of more complicated geographic operations on queries, group bys, geographical unions, things like that. So it might make sense to do that, to take a break now to about 3 o'clock, and then back at 3 o'clock we'll work back through these group bys, joins, and other things. All right, so back at 3, and we'll move to the next part of the notebook. In the interest of time, we're going to move quickly through the building areas component and move directly to the spatial joins part, where we're talking about how to relate spatial data sets together, and we'll also talk about querying for which objects are nearer to which other objects. But to do that, we still need to run the building up areas for visualization component. So if you're comfortable, go ahead and run all of the cells using Shift-Enter between building up areas for visualization down to the down to the part on spatial joins. Or you can follow along with me instead and go ahead and do that run on your own time. It's just because we're sort of, we want to make sure that all the material gets covered in a way. There's exercises for all the stuff that we've posted online for the workshop, and we're very responsive when things are posted to the repo. So if you work through stuff that we don't cover and you have questions about it, feel free to ask it in the Slack or preferably on the GitHub repository, and we'll be able to answer questions in that mode. What we're doing in that collection of code is we're taking the listings that we've got and we're building polygons out of those listings based on where individuals claim they live. So we're taking the coordinates of every single Airbnb, and then we're saying, okay, if this person says they live in this neighborhood and this person says they also live in that neighborhood, group them together. And then try and build a polygon out of all the places where people say are the same neighborhood. At the end of that process, we get a collection of neighborhoods in Austin from the Airbnb data, which are built in blue. So that whole part is walking you through how points can aggregate into polygons together, either using convex hulls or better but slightly more complicated hulls. I'm walking you through how to take a point data frame and out of that construct polygons from a group by. Okay, so that's kind of a generic operation in GIS known as moving or changing supports. And in this case, we're moving supports through a group by operation. Okay? At this point, we're working with spatial joins. So now that we've got two polygonal data sets, we've got the Airbnb neighborhoods in blue, and then we've got a set of official boundaries in red. We might want to quantify how those two sets of polygons or how the points underlying them relate to one another. And this is done oftentimes using spatial joins. Spatial joins are useful when you're asking spatial joins and spatial queries, but here we're going to be talking about mainly spatial joins. Spatial joins are useful when you're asking questions about relationships between geographical or geometric objects. And so here we're going to be talking about how many Airbnbs fall within this neighborhood or fall within this neighborhood, or how many Airbnbs that claim they're within this neighborhood are also within this other neighborhood. We'll be building some contingency tables, we'll be building some simple counts. But in general, all of this operates using these formal spatial queries and spatial predicates. The full implementation of this is known as a dimensionally extended 9-intersection model, which if you've done geographical queries before, you may have seen or heard about this set of relationships, and you may have seen it expressed in terms of some predicates about shapes intersecting or being contained within or crossing one another. Here, we'll be mainly working with the three predicates that are supported by GeoPanda's spatial join. So when we're working with spatial joins in GeoPandas, we're going to be talking about one geometry intersecting another geometry, which means do they share any points in common? We're going to be talking about one geometry containing another geometry, where all of geometry B has to fit inside of geometry A, or the flip of that relationship within, where all of geometry A has to be inside of or contained by geometry B. So these three operations are accessible through the S-join function in GeoPandas. And GeoPanda's spatial joins relate two vector data sets together in this manner. So earlier, we had our listings and our neighborhoods. And these two, dot plot. I'll do this in the other order. So we had two pieces of data. We had, sorry about this. We had the neighborhood listings, which I'm sorry, I'm doing this. We had the neighborhoods, and then we had the individual listings that sit inside of those neighborhoods, right? And we made a couple of different maps about that on the fly. To count the number of listings that fall within a neighborhood, we would use a spatial join. And here, that spatial join is saying, give me all of the listings, all of the thing on the left, that fall within all of the polygons and the features on the right. And spatial joins in GeoPandas allow us to do this kind of operation. So when you run listings and hoods, when you do this operation of listings within hoods, you get a geodata frame where it looks pretty much like listings. It's got all the information from our original Airbnb listings. But then over at the end, we have information about what neighborhood each listing fell in, right? So if we did listings in neighborhoods through the spatial join, each listing is going to have the index, and then any other column that's relevant from that other data frame. So every single bit of information about the neighborhood that the listing falls within. Okay? So this spatial join is denominated in terms of the left data frame, so all of the listings, and then it takes all the elements from the right data frame that apply to each row in the left. So if one Airbnb was within multiple neighborhoods, depending on how you configure it, you'll get multiple rows for each listing. Here, every Airbnb is in a neighborhood, and the neighborhood's data is propagated into index right, which is the index in neighborhoods which the listing falls in, and then the ID of that neighborhood. Okay? Does that make sense? When you make a call as a spatial join, which listings are within which neighborhoods, that's how that works. All right? So what this does, presented nice and cleanly here, is allow us to speak about what neighborhood and what, in our original listings data, and what official neighborhood relate to one another, right? We had neighborhoods in the original listings data, which had names like University of Texas or West Campus. And then we have information coming from an official neighborhood boundary, which with names like 78705. And this should sort of reflect kind of the different provenance, because one of these things is designed for marketing purposes, trying to give people an idea about where the neighborhood, where the listing is that they're trying to rent. And the other one is sort of an administrative function. So if we wanted to, we could try and figure out, now that we've related our point data and our neighborhood data, what the relationship is between those two polygon sets, right? We can get a contingency table of, if you're in Allendale, you might be in these other two neighborhoods in the official data. Likewise, if we just wanted to know how many pieces of, how many listings fell within a single hood ID, you could do something like this. A group by, which tells you what polygon that point was in, and then gives you the count of all the things that fall in there. I'm calling out price, but you could do ID. It doesn't matter. If you wanted to get the average price within a neighborhood, it then becomes sort of standard GeoPanda, or a standard pandas group by operation, right? So using the S join up here to go from two data frames into a single data frame that expresses their spatial relationships, then lets you treat it as before, just like a standard geodata frame.
If this was not a point but a polygon, and then portions of the polygon fell in two, then is it possible to actually say choose the polygon which has a majority of the area?
I don't think that that's...
Because within will exclude those, right? Because it will not fall in A.
You're right. So in that case, you can use intersects, right, as your method. But you don't, there's no by default way to do that. If you wanted to filter it, you could access the .area attribute of every row and then pick the one with the biggest area.
I see.
But that would have to be a secondary group by to figure out, okay, so from my original index in the left data frame, which one in the right, the result, has the largest area. So that would be, but there are multiple ways to sort of go through that. So here we're building a contingency table between the neighborhoods that the listings say that they're in, and then the neighborhoods that this other data set would say that they're in. Now that we've done the spatial join, we can just work with them as a standard pandas table. And this contingency table is built using the same sorts of group bys and unstacks that you may have learned in a pandas course. Okay? So this allows us to move from points through to polygon representations and talk about structural relationships between those things. Further, we could talk about how many unique names, how many different place names are there in any single government neighborhood. And doing that involves another kind of group by from our listing in hoods, we can aggregate up all of the things that we see in each government neighborhood, again, using sort of pandas, fundamental constructs of a group by, grab me the neighborhood that people say they're in, and give me its unique name. So these are just default pandas operations. The sort of standard way to work with these spatial joins in Python more generally is to do the geospatial join, get the object that gives you all of the structured relationships, and then later on do your aggregations or your operations. So like if you had to filter based on which one has the most area or which one has the highest median price or something like that, you're always going to run the spatial join to get the relationships, and then you're going to process it afterwards using pandas. Okay? So most of the time, the actual important spatial operation is only done in the actual spatial join command. Okay? So moving on from this part, lots of this is pandas manipulation. So here we're grabbing the distinct names. We're finding out from that how many names fall within each one of these other polygons. And this is, again, all pandas. This is not spatial manipulation at all. So we're doing this group by, we're trying to find the unique names in them, and we're doing this len. We're moving it back, and then here we're making a choropleth of how many neighborhoods do people say that they live in based on the government hood. So we're constructing this polygonal relationship between the listings and then the government relationships here. This is all sort of pandas manipulation, and we've, at the break, we're talking with some people who wanted to sort of get into more explicit spatial statistics. So we're going to move on a little bit more quickly to make sure we get to the rest of the material. Here is an example where we're talking about what are the properties of my nearest neighbor. So you might have heard of nearest neighbor queries. Spatial joins provide you some set of operations between two different spatial supports. So it says, does A intersect B? Well, then they're considered related. Is A within B? Is my listing within this neighborhood? Well, then we'll consider them related. Nearest neighbor queries are a bit different. Nearest neighbor queries or distance range queries are structural relationships between observations that try and communicate what's the average price of the nearest 5 listings, or what's the average speed limit of the next 5 roads on this path. And these kinds of operations tend to use search areas called buffers. If you've done GIS before, you've probably heard about buffers. Buffers take a geometry and expand them by a particular radius. So a buffer around a point is shown here. In each red location, we're increasing our search area by 2,500 meters. And that increased search area is shown in the blue. You can buffer things in GeoPandas using the dot buffer method. So a lot of these kinds of geographic and geometric primitives are already built into GeoPandas data frames. So using, just as an example, listings.buffer contains the way to take a geographic data frame and then increase all of those geometries by a particular pre-specified amount. So buffers are usually integrated quite a bit in geographic analyses. And let's say we had a query like, what's the average price per head in 1,000 meters around each Airbnb? So just to do a small example, we're going to be focusing on neighborhoods in the downtown. So we're going to focus on only the downtown listings. And this is for computational reasons. It gets pretty difficult to do this in large scale. So we focused in on only the downtown neighborhoods. Okay? And then if we buffer each one of those, then you can see from here that there will be once we do this together, you'll see kind of like the thing we saw before, where each observation has this large search radius around it, and then the center of that search radius is shown in red. If we made this smaller, let's say we called it 100, these buffers would be smaller, right? So that buffer method is doing that. So all of these new things around the point, all of these big circles are polygons. And stacking them together, we can use some pandas magic to grab the, or what we're doing here is we're building a new data frame using the search buffer, and we're giving the price per head in that buffer to that data frame. So we're computing the downtown listings.price and dividing it by the downtown listings dot accommodates, which contains the amount of people that the Airbnb can accommodate, and you get this indicator of price per head. Oh. Right, because it's already been converted. And then now, if we have these search buffers and we have our downtown listings, again, we can do this spatial join, and we can say, what is the average price? What is the average price of all these other listings using all of these search buffers? And when we do that, we're going to be taking all of those search buffers and looking back through all of our listings, following every single one that falls inside of that listing, and then creating another data frame that gives us a spatial join. And this looks just like the one we constructed before, but now uses this intersects operation. And again, at the end, we get the index of the other Airbnb that it matches to and the price per head at that Airbnb. So by stacking these buffers and spatial joins together, you can answer these kinds of questions. Buffering gives us a polygon that says anything within this area should be considered to my focal point in that buffer, and then we can use that in a spatial join to collect everything back up and aggregate. Okay? So when we do end up buffering and getting our average prices on that group by again, you get a data frame that looks, after you do your group by the original listing ID, you can get an average of all of the other buffers that intersect my original listing, and then aggregate by price. So like if I did listings buffer join dot group by ID, listing buffer join, and then said chunk in, just to show you what one looks like. Each of these chunks is one listing, right? So that ID is unique. So that's one Airbnb. But the index right from our spatial join is the index of every other listing within 1,000 meters. When we aggregate the price per head out of all those listings, we get the average price per head in 1,000 meters. So again, once we do the actual spatial operation, all the rest of this is pandas group bys and descriptions of that original spatial structure. Okay? Now, some of you may be interested in performance, and I'm not going to walk through this, but there was a reason why we filtered down to the downtown listings. The Airbnb data set overall is 11,000 observations. And waiting for that to happen on a laptop for 11,000 observations is quite difficult. So using SciPy Spatial, there are special high-performance methods to compute spatial relationships. And this, the KD tree, and its Cython implementation, are really efficient ways to do that. I detail that at the end of the notebook if you want to go through and do that. But I think for time purposes, we'll skip the high performance part and leave that to another day. So if you'd like to read that on your own time or ask questions in the repository, we do detail how to scale this kind of stuff up. But that's the reason why we sort of shrank the problem down when we were talking about what's the average price or price per head in the downtown area. So at the end of this notebook, it's a lot about how to do that, that price per head stuff. So if you'd like, we've come to a bit of a juncture here. There's a problem set that we can work on together. We can sort of you can solve the problem set, and we could go through it together. But this basically checks the understanding of most of the main concepts from our previous lecture. So we could do that, or we could take a short break to retool and then move on to the statistics. If you'd like to do the problem set, raise your hand. Okay, let's move on to the statistics. Cool. So, Serge, you want to come?
Just to reiterate, so the problem sets also have solutions in the repository, so you might want to look at the solutions after you bang your head against the wall for a little bit, but don't look at them initially, because if you're like me, I don't learn much when I just look at the solution. I have to bang my head a little bit. Okay, what we're going to do is shift gears a little bit here once I get this going. So I'm going to move to GDS3, the notebook, entitled Geography as Feature. Much of what Levi covered earlier in the first sections is basically called deterministic spatial analysis. You're looking at the spatial relationships, be they intersections, joins, containment, between geometric primitives. Okay? And the Shapley library under the hood is the key part that GeoPandas is using to implement that. That's not the extent of geospatial data analysis. Very often we have attributes for each of these geometric units, be they points, lines, or polygons, and we want to understand the statistical distribution of those attributes and how it relates to the spatial distribution of those features. And spatial analysis is about really putting those two things together. So we're armed with basic concepts of deterministic spatial analysis. Now we want to sneak up on probabilistic spatial analysis, that is geospatial statistical analysis, that takes the geometric properties of the data into account. Okay, so that's a mouthful. So we're going to start to think about, in say machine learning parlance, treating geography to create new features, if you will. So new variables that express spatial relationships that we then incorporate into the statistical analysis. We're importing a bunch of libraries, many of which Levi talked about already or covered. The new ones that we're going to deal with in the second part of the talk has to do with a library called PySal, which is a library that we maintain. Its goal is to do spatial statistical analysis of a variety of flavors, right? So we assume that we have things like GeoPandas and Shapley to deal with geoprocessing and getting the data in the format that we need. When PySal started a long, long time ago, things like GeoPandas, Shapley didn't exist. So we spent a lot of time writing shapefile readers just so we could bootstrap the statistical part. But the world's a much richer place now, and we have these excellent geoprocessing libraries. So we're going to be using some of the same data that we've built up already. We've cleaned up the data. We've changed the support from points to polygons. And we're going to read some of it back in. So we're starting with the listings data that we've seen earlier this morning. We're going to pull contextually in and do some plotting so we know what the context is. So we have two layers here. We have the point layer for the listings, and we're using color to denote the price of the listing. And we also have the neighborhood boundaries, the polygons. So if you're an urban economist interested in housing markets and what explains the spatial distribution of those colors, you want to leverage the methods that we're going to be talking about this afternoon. One of the key constructs in spatial analysis for this type of data are so-called spatial weights that are going to allow us to express potential relationships between the spatial observations, whether they are polygons or points or edges on a network segment, segments on a network. And you can think about this notion of a spatial weight as an adjacency matrix if you're familiar with social networks. So it's a big matrix. Let's say we have n polygons, 100 polygons. Where our matrix is going to be an n by n matrix where the values in row I, column J of that spatial weights matrix tell us about the potential spatial relationship between polygon I and polygon J. Now, two things to note about this. What those values are is yet to be determined. Are they going to be binary? Are they going to be continuous values? And we'll cover that. And then secondly, we actually never store the full n by n matrix because many of the values would be 0, and therefore we don't need to store that. So we're going to leverage sparse representations of these weight matrices. Right? But conceptually, you can think about them as adjacency matrices. This is a neighbor of that, based on some criterion. All right, and in PySal, we spent quite a bit of time making these efficient and scalable. But under the hood, the attributes of the spatial weights, there's two dictionaries that we start with. A neighbors dictionary that tells us for each unit, say each polygon, who are my neighbors. So the value for that dictionary, for the key value pair in the dictionary, is the ID of the focal unit, the focal polygon, and then the list is simply the IDs of the neighbors to that polygon. So in this contrived example, we're creating a neighbors dictionary, and we have 3 polygons labeled A, B, and C. And their neighbors dictionary, well, A is a neighbor of B, B is a neighbor of A and C, and C has only one neighbor, B. So you can think about 3 polygons in a linear row. Okay. So we have 3 polygons. This expresses who's a neighbor of who. That's the neighbors dictionary. We also need the value of the weights. So these are the values that go in the IJ row of the weights matrix, if we indeed have the whole weights matrix. And it's up to us. Right now we're saying, well, the weight for the relationship between A and B is 1 for that neighbor pair. But B, its neighbors are A and C, and we're going to assign a different value for the what's called a join between A and B. It's 0.2 from the perspective of B's as the focal unit, and 0.8 for B's relationship with C. And then conversely, for C's relationship with B, its weight is going to be 0.3. Okay? So we have these 2 dictionaries, the neighbor dictionary, which tells us who's a neighbor of who, and then the weights dictionary that tells us something about the value, if you will, of that particular neighbor pair relationship.
Is that necessarily symmetric? If A is a neighbor of B, is B a neighbor of A? Is that?
In this case, they are, in terms of the notion whether they're neighbors, but the weights, in this case, for that pair are not equal valued, so they're not symmetric. And we'll see examples where we do have symmetric neighbors and other cases where we don't. Okay, so that's a toy example, just to get our heads around what the underlying data structure for the weights class in PySal is. And that wouldn't be much use if you had to do this by hand for a map with, say, 11,000 points for the listings. It would be a royal pain to do that, right, by hand, write out what the listings are. So PySal leverages now GeoPandas and related things where we can read these different spatial formats that Levi mentioned this morning, or earlier this afternoon, and build the weights matrix from the original data. And we'll do a couple examples of this. Okay, so here I'm just finishing up with our example. LP is libPySal. We call the weights module the class is W, uppercase W, and if we pass in the neighbor's dictionary, we get back a binary weights object. An instance of our spatial weights, its weights attribute is our dictionary, right, which has the weights. We could also pass in both the neighbor's dictionary and the weights dictionary, and then the weights are no longer binary in the first case. So if you don't pass the weights in, you only have our required required argument of the neighbor's dict, you'll get back binary weights. If you don't want binary weights and you have information, you pass that in as a keyword for the weights. Okay? So there's different ways to get the values for those weights. And this is an industry. People are coming up with new ways to do this all the time. We're going to start with the simplest, which are contiguity weights. So whether I and J are neighbors is going to be based on a contiguity criterion. And that seems simple at first glance, but it's actually more complex once you peek under the hood. And here we're going to leverage Shapley and GeoPandas. So backing up for a second, contiguity, do things touch? Touch, again, conceptually seems simple, but programmatically it's not so simple. What do you mean by touch? All right? And in deterministic spatial analysis, if we're dealing with shape files where we have a polygon represented as a bunch of xy coordinates for one polygon and a second polygon that has xy coordinates, our contiguity criterion is going to use those coordinates in different ways. The simplest way to think about this is if you had a checkerboard or a chessboard, right? The different notions of contiguity have to do with the way certain pieces can move legally on the chessboard, right? So queen, if you think about the center cell in a checkerboard, which way can a queen move legally? How many moves could you make from a queen position?
Move anyway.
What direction? So you can go north, you can go northeast, east, southeast. So the queen can move 8 ways, right? So queen contiguity for that center cell would be any of the polygons that share one of the vertices of the queen's, one of the vertices or an edge of the queen's cell, the center focal cell. Okay, so that would be queen contiguity. Rook contiguity is if the way a rook could move is north, south, east, west. So the rook would not have the off-diagonal neighbors. Working that back to the geometries themselves, in real-world maps, we typically, unless you're working with rasters, but if you're working with vector data, your maps are not regular sized or shaped polygons. Think about the counties of the US, they're very different animals. Okay, so now we want to map this notion of queen and rook contiguity to an irregular lattice, a map that has irregular polygons. For queen, what we look for are simply 2 polygons that share at least one vertex, the XY pair or lat lon pair. They would be queen neighbors. For a rook, it's more complex. They have to share 2 consecutive points that define an edge, a common edge. All right? So PySal lets us build a queen neighbors spatial weights object by passing in a data frame, our neighborhood's data frame that we've been playing with earlier today. We just read that in, and that's our argument to the queen from data frame. And that gives us a queen neighbors. Got to spell it right. Okay. So it does the hard work for us. It's reading in each row of the data frame, looking at that geometry column, building a spatial index, and then checking what polygons I should test for a common shared vertex, 1 or more. And when I find them, I build the weights and the neighbor dictionaries and populate the object. Okay, we can plot these to see what this looks like. We have our polygons, the neighborhoods. We're using the centroid of the polygon as a representative point. And then we're drawing an edge between 2 centroids of queen neighbors. Okay, so that's our adjacency graph based on queen contiguity for the neighborhoods in Austin. All right? Questions on on that so far?
And this one, is this an undirected graph?
Yes, these are undirected. So we're making no difference between A to B, B to A. Other handy things that the W object does is check if you have disconnected observations. And these are called islands. You could be a true island. So if you were looking at the, some of the county geometries for the US have the Channel Islands in California as separate polygons, and they don't share vertices with the mainland. So they are both physical islands, but geometrically they're also islands. And that means they have no neighbors in this weight structure, and that can cause problems for certain types of spatial statistics that we'll get to. So you want to know if you have any neighbors. If you do, there's ways to attach them. If you're then going to move on to spatial analysis where you need where you cannot have islands, right? But fortunately for the Austin neighborhoods, we don't have any islands because that's an empty list. If there were islands, it would tell you which rows in the data frame are the ones that don't connect by this neighborhood criterion. All right? Yeah.
So that weight is either 0 or 1? The weight is either 1 or...
Yes, so for this constructor, when we're calling queen from data frame, it's binary contiguity, right? So right now the weights are all ones or zeros.
And 1 is connected, 0...
Yep. All right, so that's very sparse. We could visualize the full matrix if we wanted to get a sense for what this looks like. All right, so we're using an image plot here basically to visualize the matrix, if you will. So these are the IDs of the polygons, our neighborhoods, and then where there's a yellow cell, that represents a join, a neighbor relationship between I and J. Okay, so this is pretty sparse. The purple, I guess it's purple, those are zeros. And that's why we don't store the zeros. So we typically work with the sparse representation because it's efficient memory-wise and compute-wise. How sparse is our object? The W object, the queen neighbors, is 12% non-zero. So only 12% of that matrix would have values, non-zero values in it. All right, and this is a pretty dense matrix, actually, in this case. All right, they're all the same for the non-zero values. They're all ones. They're binary. And we can check other properties of our graph. For those of you who are interested in graph theory, we don't have any islands. So every polygon has at least one neighbor, one queen neighbor. But you could still have multiple components in the graph. Right? So you could have a bunch of connected components in the bottom and at the top. And we want to know that as well because certain types of spatial analysis require a single connected component, meaning you'd be able to travel to any of the polygons by passing through neighbors. Right? If you have more than a single connected component, that won't be possible. You won't be able to travel from one group to the other through the contiguity graph. So we can check that down here. We only have one connected component, and they're all belong. Zero means you're in that first connected component, Python zero offset. Right? If there were multiple components, you would see which component each polygon belonged to. All right, skipping over this, we've given this workshop, versions of this workshop with other data sets. We typically change it to where we're giving the data sets, giving the talk. And last time Levi and I gave this was in Berlin. And Berlin's adjacency structure is very different. So there were multiple components. There's different ways to represent the weights information in the weights object. So we can convert from our PySal W object to get an adjacency list that could be useful for other downstream applications. So here we create a data frame, adjacency list, and look at the head. So we'll have 3 columns in that data frame. Focal, which is the ID of the focal neighborhood, focal polygon, and then the ID of one of its neighbors. So we're exploding the weights object into a data frame. And then the value of the weight, which are all going to be 1s in this case. Okay, so this is our adjacency list, or at least the top part of our adjacency list. And this is going to be handy to construct other geographical features for the spatial analysis that we're going to be doing. Okay, this is I read the listings data in. Levi cleaned it up before. I'm going to clean it up again because I didn't read it in the clean data. So just skip over that. And assign that cleaned up price to the listings data frame. All right, now we're going to make use of some of the information. Let me close this part over here, make this bigger. Got a lot more room there. All right, so we cleaned up our price data. We have this new column in our listings data set. Well, we haven't put it in yet. Price. There we go. We add it in. Okay, now we have the cleaned up price for the listings using some of the techniques we covered earlier. We want to get the median price in each neighborhood. So we're going from the points to the polygons and creating a new attribute for the polygons, the median price. Right, we do that with a group by. Okay, and we're going to attach the index right on the index right, and we call price.median. We're calling the median method on that price column. And we're grouping by the neighborhoods. Right, so for all the listings in a given neighborhood, get me the prices and then take the median and return that. And put it in median prices. Okay? That gives us a 44 comma, so there's 44 neighborhoods, and those 44 values are the median of the listings in each of the 44 neighborhoods. Okay, let's put that into our neighborhoods data frame. So we're doing a merge where we're taking the median prices, creating it to a data frame or converting it to a data frame, and then we're going to do a merge with the neighborhoods data frame and plotting it. So visually what we see now is instead of the points nested in each of the neighborhood polygons, we've done a change of support where we've taken the median of the point listings in each of the polygons and used that to develop a hue or choropleth classification for the map. Okay, so the yellow is the highest median price for that neighborhood. That neighborhood has the highest median price, and the darker hues, lower values. Okay. Questions? All right. This gives us a different visualization of the same market, Austin, than we saw in the point data. The point data is very rich, but there were 11,000 points, which is a lot of information to process cognitively. So one reason you want to aggregate like this is to simplify the cognitive load, and hopefully you do so in such a way that you're capturing the overall structure and not throwing away too much information. We're throwing away a lot of information by going to the median, but what we gain, hopefully, is sort of a gestalt, if you will, of the spatial structure of the market. Once we have that visualization, we then want to start to ask questions about, well, what's the relationship between the prices in this neighborhood and in the neighboring neighborhoods? Is there a relationship? And is it constant over space? Right? Is there so-called clustering in the data set? Or are these maps random? Right? And much of what we're going to do the rest of today is look at the methods that allow us to answer those questions from different perspectives. Okay, so does this look random to you? Why not?
Clear and high price in the middle.
Mm-hmm.
Downtown Austin.
Okay, so this stands right out, that yellow. Right. What does random mean to you in this context?
Should have in different yellows in different locations.
Okay, you might expect more in the different classes, more colors, more polygons with more variety in the colors, and their locations being random. All right, so it's a hard thing to unpack, and we're going to try, hopefully unpack it the rest of the today.
So the yellow is the highest price.
Mhm.
And is there any visualization you can attach, like how many data points in that region?
Yeah, we're going to get to that, for sure. Yeah. Right. The other things that make this difficult, one, we're going to have to formalize what do we mean by random, okay? But visually, it's complicated because these polygons, these neighborhoods are not all the same size or shape. Right? And our eyes get drawn to the large polygons, even though statistically speaking, each polygon has a value. It's one observation. Right? So conceptually, again, it's hard just to rely on visualization to answer that question. So we're going to couple it with analytics. What we're going to do here is using that notion of the adjacency list, where we have the focal neighborhood and one of its neighbors, the focal neighborhood, its other neighbors, and so on and so on. We can start to look at the relationship between the price, the median price in the neighborhood, and the median price not for all its neighbors, but for each of its neighbors. Okay, so for example, our adjacency list, we chained together a couple merge operations here so that we're building more columns in the data frame. So we have the focal neighborhood, neighborhood 0. One of its neighbors is 25. We know the weight from the queen. We know the ID of the focal neighborhood from the original neighborhoods data set. We know the price for the focal, meaning the center neighborhood in this pair relationship. And then for one of its neighbors, we know the price for that neighborhood. Okay? But each polygon may have more than one neighbor, so we want to look at all those pairwise relationships. So that same focal unit has 3 neighbors, 25, 3, and 21, and they all do not have the same price. Okay? This focal neighborhood is going to have the same price for each of those joins. So we're interested in the relationship between the median price in the focal unit and the median price in the neighboring units. So we can take the difference between each focal unit and the neighborhood units, the neighboring units. For example, 0 focal unit, neighborhood 25, the price difference is -60, meaning that the price is higher in the core. As you move to the neighbor, it drops by $60 a night. Right? And we do this, we're building this new variable up in the previous steps. All right? So we're constructing a new feature, if you will, the price difference between the focal unit and the neighboring unit for each of the neighboring pairs. Then we can query that, and we find that there are some neighbor pairs where there's no price difference. So you have neighboring neighborhoods where the median price is the same. We can find them leveraging simple pandas queries. But at the other end, we can find the contiguous neighborhoods where the price difference is large. Right? Again, leveraging pandas, as Levi mentioned this morning. We do the spatial operations to build new features and embed the geographical relationships, and then pandas queries to query those. Okay? All right, so that is contiguity for polygons. Do you share a border? What do you mean by share? Well, do you share at least one vertex, queen neighbors? We could have done the same thing for Rook, changing the function that we called, and it would have been slightly different because Queen and Rook have different sparsity properties. You're going to have typically more neighbors if you use Queen because it's a less stringent movement criterion than Rook. But as we've seen earlier, one of our data sets was the listings, the points themselves. And we might not just be interested at say, the neighborhood level, what's the relationship between the median price in this neighborhood and median price in the neighboring neighborhoods, but how about the individual listings themselves? What's the relationship between the price for this Airbnb and the ones that are, quote, neighbors to that? All right, so that's what we're going to talk about now. So we'd like to be able to use the same notion of contiguity, but for points. Build a spatial object, a spatial W object for points. And there's multiple ways to do this. We're going to use what are known as Voronoi polygons. So those are the 11,000 points, plotting the price. Right? And we want to consider how the price for one Airbnb may be associated or related to the price in the neighboring Airbnbs. So we're down to the micro level here, not at the macro neighborhood level. PyCell has a function called Voronoi frames. So Voronoi polygons, are people familiar with these? Right? For a point set, they're going to partition the plane into mutually exclusive polygons, where each point is the so-called generator point for the polygon. And that means each point has a polygon defined around it such that any other point that would fall in that polygon, that generator point is the closest point in the rest of the data set. If we look at pictures, it should be clear. So here's our neighborhoods, and we've drawn them on top of the Voronoi diagram. This is the Voronoi diagram. The edges, you go out until the edges intersect, and some of them takes a long time to go. So this little black dot is basically this area, because it's a very different scale. So we have to clip this diagram by our extent of our study area. And this may take a little bit of time. We're going to clip by using what's known as clipping. So we take the extent of all the neighborhoods, we're blending them or dissolving them together, and all we care about is the exterior of Austin boundary. And we're going to use that to clip the Voronoi so that we don't have to go out to infinity. So that's our clipping polygon. Then we set the coordinate reference system to be the same because this is a spatial operation. And the thing that's running is we're clipping the Thiessen polygons, which go out to infinity, with our clipper polygon, the one we just made, which was the boundary, if you will, of Austin. And then it creates a new geoseries that's 11,000 polygons. So there's one polygon for each of the listings now. And they've been clipped, so some of their edges don't go out to infinity. What do these look like? Okay, so that's the Voronoi polygon for the first listing. If we plot those and you squint, those are the 11,000 polygons, the Voronoi polygons. So each listing has its own dominant area, if you will. If you dropped a pin in the Thiessen polygon, the closest listing is the one that generated that polygon. So this is nice. Voronoi polygons are very useful. For our purpose, now we're back in business if we want to develop spatial contiguity matrices because we now have polygons. We're no longer dealing with points. So we could say, well, give me the queen neighbors for this, or give me just Voronoi neighbors, those that share an edge. Saving it to disk as a geo package. And there are 11,000 polygons, so when we try to view it, we get a blob of the edges towards Austin. So we're going to zoom in on a particular neighborhood, Hyde Park. Anyone from Austin? Okay, so Hyde Park is north of University, I think. Pretty nice neighborhood. that has 158 of the neighborhoods. And if we're just subsetting that, so that's what the Voronoi polygons look like for the listings in Hyde Park.
Because the size of each polygon is different, right, for each point?
Sorry?
The size of each polygon for each point may be different, right? So it's not the same as, let's say, I just buffer all the points.
Right.
They will convert into polygon and then do contiguity relationship between those.
Right. So the size and the shapes of those polygons are a function of the spatial distribution of the points, right? Not the values of the listings at the points. So these are just purely geometric partitioning of that plane based on where the points are. So the larger polygons mean what? Fewer points in the neighborhood, right? So the distance, as Levi talked about the nearest neighbor distances, those are going to be larger, if you will, for the generator points that are associated with the larger polygons.
Just a minor detail, I noticed the driver was missing when you're saving it to the geo package.
Yeah,
That just created a directory of shapefile stuff.
that's news to me. Where did it create the directory?
So the path that you gave it was seasons.geopackage, and I just checked that, and it seemed like that was actually a directory that had shapefile stuff in there without the driver.
Without the driver to generate them or to read them?
So with the two file, you didn't have driver equals GPKG on there when you did two file. And so I listed the
Ah.
directory of that location, and
Yeah.
without the driver, it just created a directory of shapefiles.
Okay. I'll have to dig into it off the top of my head. Okay, so there's Hyde Park. And then we're going to plot, here we're zooming in on the bounding box of Hyde Park on the left. That's all the listings in the data set just clipped to the bounding box of Hyde Park. Those are the Voronoi for the listings in Hyde Park. The colors are the value, represent the value of the listing. And that's the adjacency graph for those Voronoi, to give you an idea. Just like we did the adjacency graph for the neighborhoods, here we're doing it for the points. Okay? Questions on contiguity type weight. So we did them for polygons, and we did them for points. All right, I'm going to skip over this, just say a couple words about it. There's other ways to define weights. So you can use distance relationships, say nearest neighbor relationships. So you could have binary distance relationships. I'm going to define as a neighbor any 2 points that are within 1,000 meters of each other. Right? So then we do a buffer around each point that has a radius of 1,000 meters. And for any other point that falls in that buffer, they're neighbors. Okay? So we get a binary matrix, but it's based on some distance cutoff. We could then say, well, we don't want binary. What we'd like to do is weight the further away properties or listings less than the closer by listings. So even though 2 of my neighbors may be within 1,000 feet of my listing, the one that's next door, 20 meters, should carry a larger weight than the one that's 999 meters away. And we wouldn't use a binary weight, we would have some distance decay to the weights. Okay, and there's ways to do that with PySal, using different types of kernels for the distance decay that allow you to be more flexible with the weights. All right? So, let's see, how are we doing time-wise? 4? Visualization real quickly, just a couple of points. We did a couple of choroplasts during the first half. We're going to just quickly go over them here because we're going to need them when we want to start to test for this notion of spatial dependence, spatial autocorrelation in the data. So this is GDS4. So GeoPandas, if you call a data frame that's a polygon data frame for the geometries, and it has a continuous attribute and you call plot and say column equal to prices, it'll do a choropleth map of that, and we'll look at an example in a second. And it's under the hood, it's using a library called Map Classify, which provides classifiers for an attribute that determines how many classes for the choropleth and how do you determine the breaks for the classes. So I'm reading in our listings. And we're first going to look at the statistical distribution of the median prices of our data. And we saw the histograms earlier today. So this is a distribution plot. It shows us the median price, the statistical distribution. Right? There's no geography here. This is just looking at a column of numbers and summarizing it the way a statistician would summarize it. Since we have that in a geodata frame, when we call dataframe.plot and we tell it plot the column median price, we get a different distribution. It's a spatial distribution. So this is using a quintile classification for the median prices. So quintiles, we take the data, we sort it, and we're going to break it into fifths. Right? Those become the bins for the classification. So that's the default. We can make it a little bigger so that it's a little clearer what's going on. There should be roughly the same number of polygons in each color group. Right? So if it's quintiles and we had 44 neighborhoods, divide 44 by 5. Right? It doesn't work evenly, but you get roughly that amount. Now we have more visual information to start to think about this notion of randomness. Right? These are a bunch of polygons that are yellow. They're at the top end of the distribution. These are not randomly distributed. Even though the geometries are weird, they're not regular pixels, we can still intuitively see, well, they're close together. They're not peppered around the map. And similarly for the dark blue and the green. Okay, we can add some legends, which can be helpful, make this a little clearer. Okay, so PySal uses, well, PySal, Map Classify comes from PySal. We use closed intervals for the upper bounds of each of the classes. So to be in the first class, you have to be less than or equal to $80 a night. To be in the second class, you have to be above 80 to 100. And in our trim data set, the maximum neighborhood median price is $335 a night. Okay, so that's how the binning works for the default. We can change, instead of quintiles, quartiles. So you change K, you get a different number of classes. So now it's only 4 instead of 5. And you can monkey around with the color schemes if you choose. There's a rich literature on choice of color schemes for choropleth mapping, having to do with what is the measurement scale for your variable. Is it interval or ratio scale? Is it categorical? Is it diverging? And there's guidance on how to do that. All right, so we could pick different color schemes to see the impact. Or we could change the classification scheme. Quintiles is the default, but there's many classifiers you could use. Here we're using equal interval, the second one, where the width of each interval class is equal. Okay, not the count of how many observations are each class is equal, that's quantiles. This is the width are equal. And then Fisher-Jenks is an optimal classifier that tries to minimize the amount of heterogeneity for the listings that are grouped together and maximize the difference between the classes. Map Classify, which GeoPanda uses under the hood, doesn't really plot. It wasn't intended to plot, but it was to give you, if you call equal interval, pass in a variable and tell it you want 5 classes, it returns an object that gives you what basically then goes into the legend of your classifier. In this case, the legend of the map. All right, so you have plenty of options for exploring the data sets. What classifier you should use is related to the statistical properties of the data. Okay, so we have classifiers. I'm going to run through this quickly. Down at the bottom, there's a box plot classifier, which is useful to identify outliers in your data set, either high or low outliers, which is a good exploratory technique. There's a heads tail break. If you had distribution that was like a power law, you don't want to use quintiles. So there's distributions that could be more useful given the statistical properties of your data set. All right, questions on map classify? All right, so then we're going to start the statistical analysis. So we looked at the maps and we asked ourselves, do those maps look random? Either the point maps or the neighborhood polygon maps with regard to where the high values are. And if the maps are not random, visually, we would like to have statistical tests that confirm our visual inspection. All right? We want that not just because it's a hip thing to do, but because visualization is really, really powerful. Our brains are pattern recognizing machineries. Right? We all wouldn't be here unless our ancestors on the plains of Savannah had really good pattern recognizing abilities, right? So your great-great-great-great-great-great-great-grandmother is out harvesting on the Savannah. She looks over at the brush and she sees the winds blowing and she sees something solid behind the wind, blown wheat or whatever it was back on the Savannah. And she thinks, well, that might be a lion or it could be a boulder. What did your great-great-great-great-great-grandmother decide? If she was faced with that decision, is it a lion and should I run away? Or should I just think it's a boulder and stay here and go about my day? What would you do? If it was me and there was a 1% chance that thing was a lion, I would run, right? And if our ancestors didn't run, our species might not be around. And that process has worked over generations and generations. So we're really good at detecting patterns. Really good at detecting patterns. That's why maps are so powerful. But they could be too powerful because there's not many lions left on the Savannah, number one. Number two, we don't do that much anymore, right? But we have this hardware that we've inherited. So these quantitative measures we're going to use in conjunction with the visualizations so that we don't fool ourselves. We don't let these powerful things run us astray and identify a cluster when it's in fact not a cluster. Right? That's the idea here. And this concept is known as spatial autocorrelation. All right, so spatial we've been rattling on about it all day, all afternoon. But the autocorrelation is something we want to unpack. So correlation is about the linear association between two variables. Right? Height and weight, are they correlated? Positively, yes, typically. All right? But autocorrelation here means you're looking at the correlation of the same variable, autocorrelation. And in our case, we're going to be looking at housing prices as the variable of interest. We want to understand its spatial autocorrelation. So what is the second variable in the correlation sense of the word? We're going to build that up. Okay? It's not spatial correlation. Spatial correlation is when you have a map of, say, crime rates and police expenditures. Those are two different variables. You can correlate them. That's spatial correlation, but the correlation is traditional. Here we're talking about something different, spatial autocorrelation. So we're going to use the median price data, build it back up. And here's our data on a bigger map. And I've changed the color scheme so that now the darker hues are the higher values. These are quintiles. All right, and I'm asking myself, are housing prices randomly distributed across these neighborhoods? Right, that's the question. Well, to me, it doesn't look to be the case. Like there's the highest quintiles, the dark blue, tend to be co-located. Right, they're over here. And the light green dominantly up here, and these blues are clustering down here. Right? But again, remember the lion and our ancestors. So spatial autocorrelation is going to do two things for us. It's going to compare two types of similarity. First one is attribute similarity. Are two housing values similar or not? If it's $100 a night versus $300 a night, that's a difference of 200. Is that similar or not? Well, it depends on the distribution in our data set. 100 versus 150 is closer together than 100 versus 300. So there's this notion of attribute similarity. How different are the values, irrespective of where they are? And then spatial similarity. Okay, where are you measuring those two prices? And are those locations spatially similar? Okay? And that's where this notion of the spatial weights come back into play. The spatial weights are going to allow us to develop a new spatial feature called the spatial lag, which is the average of the housing prices, or the listing prices, in the neighboring polygons. Okay, so that is nothing more than a weighted average, where for each neighbor to polygon I, we're going to take the median price in that neighborhood and multiply it times a standardized weight, so that when we add up that weighted average, when we add up that sum of the products, we get a weighted average. And that becomes what's known as a spatial lag for the focal polygon. It encapsulates all the information in the surrounding polygons into one value. And that becomes our second variable for the correlation. So now we're going to correlate the value for the listings, median listings in a neighborhood with the average median in the surrounding neighborhoods. And we do that for each of the 44 polygons. So that is basically a correlation, but we've created this spatial feature called the spatial lag. And that's where the auto comes from, because it's still a housing price, so it's the same variable, but this new variable is spatially constructed. So to get the lag, we take the original variable from our data frame, median price, and we call libpysal or lp.weights.lag spatial. And you pass in two things, your weights object, we're using the queen that we saw earlier, and the median prices. So it basically takes the weights matrix and multiplies it times a vector of prices and gives us a new vector, which is the average in the neighborhoods, the neighboring neighborhoods. Okay? So that's our new feature, ylag. So that first neighborhood, whoever it is, the average of the median prices for the neighbors of that neighborhood is $115 a night. The last neighborhood, whoever that is, the average in the surrounding neighborhoods is $154 a night. That is just another attribute, so we can make a map of the lag, the spatial lag of the median prices in the quintiles, and put them together. So on the left, you have the original choropleth quintiles for the price, and on the right, you have the spatial lag. And spatial autocorrelation is going to test whether those two maps are correlated, loosely speaking. So we created this new one using the spatial operations. Questions on the lag? So it's similar to the notion of a time series lag. Anyone go to the time series tutorial? It was this morning, I think. It's a popular one. So in time series, the sales price in February is related typically to the sales price in the previous month, January. So January is the first order lag to February. February is the first order lag to March, if we had a monthly model, and so on. But time is much easier than space, because in time, the recursive array goes one way, one direction. The future doesn't influence the past influences the future. And everybody has one first order neighbor, one and only one first order neighbor. In space, it's much more complex. If you think about the center polygon, how many neighbors does that center polygon have? Well, it's hard to squint. Does it have one neighbor? There's more than one neighbor, right? Number one. Number two, it is a neighbor of its neighbors. So what goes on in that polygon influences what goes on in the neighboring polygon potentially, but what goes on in the neighboring polygon can feed back. So the neighboring relationships for the spatial relationships is much more complex. It's multidimensional, and it could be simultaneous depending on our time frame. Whereas in time, one neighbor and one direction. And I bring that up because when people started doing spatial autocorrelation, developing methods to estimate regression models that incorporated space, the econometricians, the time series econometricians said, well, this is silly. We have this massive literature on time series econometrics. Let's just use that. And that made sense because you had, if stuff exists, why reinvent the wheel? And the reason it doesn't work is you'll see papers even today, people studying, say, the relationship between school expenditures and school performance in the states and the US, and the data comes alphabetically. So you have Alabama to Wyoming, and they'll use a Durbin-Watson test for temporal autocorrelation because they'll pretend like Alabama came before whatever's next, Arkansas. And literally this happens. So clearly that's not how geography works. It's more complex. So you can't just use the straight off the cuff time series methods on spatial data, which shouldn't be a surprise, but it still happens.
So when you do the autocorrelation, there will be an overlap between the spatial data?
When you do
Like
the time series methods on spatial data,
Right, I mean, so when we do the median price for the neighbor's neighbor, and that neighbor would have the same neighbor from the other neighbor, and that median price would be the same. So the spatial data would be similar polygons and everything would be same, right?
not the same, but this map is a little bit smoother, the one on the lag,
Okay,
so, because it's taking an average, it's borrowing information from the surrounding ones.
so,
Yeah. So it's not purely a simple correlation, because by construction, these values are going to be autocorrelated, even if the original variable was not autocorrelated. So these tests that we're going to talk about now take that into account. So now we're going to develop the test that, it's a statistical test, whether this map is random or not. And there's two families of these things. There's global test that we use to answer the question, is this map random or not? Okay? Then there are so-called local tests that allow us to assess whether there's different types of clustering going on and subsets of the data, identify hot spots and cold spots, things like that. But we'll start with the global one. So by global, one statistic for the entire map, answering the question, is the map random or not? And we're going to develop this starting with basics, and hopefully it clarifies what's going on here. So we're going to take our data set, the median neighborhood median price, that's our variable of interest, that's what the map's showing us, and we're going to convert it back to a binary variable. Right now it's a continuous variable, but just to get the main concepts down, we're going to create a binary variable, whether the neighborhood's median price is above the average or below, whether the neighborhood median is above the median of the medians. Is it high or low? Okay, so the median across the 44 neighborhoods was $109 a night. We're going to create basically a dummy variable, YB. If the neighborhood price is above 109.25, we're going to give it a 1. If it's below, it's 0. So we're creating a binary variable. So we have 22 neighborhoods above the median, 22 neighborhoods below the median. And then we're going to plot that. Okay, so the black polygons are the ones where their price is above our threshold, the median. The white polygons are where the price is below, the listing price is below. So far, so good? And I did this on purpose. So black was picked on purpose and white because the statistics we're going to use are called join counts. And they conventionally call black and white, as we'll see in a second. So the join counts count up the different types of joins. and compare them to what we would expect if the process that generated our data was a random one. Okay, so we're going to have this conceptualization that our null hypothesis, if you will, is that whatever generates the maps that we see is a random process, completely spatially random. So we're going to develop a distribution for that process, a random process, and use it to compare what we actually see, the map we actually got, and say, does this map look like it came from a random process or not? Okay? So the join counts are the way we do this. What is the join? A join comes out of our W. If Wij is 1, it means that's a join. You have one polygon that's a neighbor of another polygon. Okay, so the joins, how many joins there are, that's a function of what you use to define the W. Did you use queen contiguity? Did you use nearest neighbor? Whatever you use, we have this W matrix that's ones and zeros. So wherever there's a 1, that's a join. But there are 3 types of joins with respect to the attributes. So if we look at this polygon and that polygon, this polygon and that polygon, that's a join because they share this edge. But one of them is below the median, one of them is above the median. So this is a BW join, black-white join, or white-black join. You have value differences for that join, right? One is high, one is low. So that's black-white or white-black. We also have white-white joins. So this join right here is a white-white join. Low next to low. So value similarity next to spatial similarity. These are spatially similar because they're contiguous, and their value is similar based on it's a white-white join. And then the third type are black-black joins. You have a neighbor pair, that's a join, and they both are classified as high. Okay, so we know the number of joins, that's in our weights matrix, and we decompose those joins into how many are black-black, how many are black-white, how many are white-white, given that we know the probability of being black is 22 over 44, or 50%. Right, so if you had this process where you're sampling from 44 to Bernoulli, you have 44 slots, you flip a coin, if it's heads, this is a black cell. Move to the next one, flip a coin, it's heads, so that one's a black cell. You do that for each polygon, that's a random process. That's going to be our null hypothesis. Because we know half the cells are going to be black, half are going to be white. But where they are is the central question in our hypothesis. So these 22 black polygons sure don't look like they're randomly distributed to me. So let's count the joins. PyCell has a module called ESDA for exploratory spatial data analysis that has these autocorrelation tests that we're using. So we import that. We create our binary variable, YB. I'm doing it again just to be explicit. I create a queen weights object from the data frame. So that reads the polygons in, the geometries, builds the W object. So now we know who's a neighbor of who. We then transform the weights to be binary, meaning I don't want to row standardize them. I'm not doing a weighted average like we were for the lag, and we'll come back to that. What I want now is I actually want to keep the binary weights binary because I want to count how many black-black, how many white-white, how many white-black. So the transform property of the weights allows you to change the weights. Either row standardize them, column standardize them, or set them to binary. I want to make sure they're binary. Then we're using NumPy. We imported NumPy as NP up above, and we set the random seed generator. Why? Well, we're going to use computationally based inference to decide whether the counts that we got for these 3 types of joins are different than what we would expect from a random process. And the way we do that is with what's known as spatial permutations. We're going to create fake maps where we pick up the 22 black cells and randomly reassign them. Okay? And that gives us a new map, a fake map. Then we calculate the join counts for that fake map. Now we have two realizations. Our original map, that one, and we know the split. We'll get to the split in a second. And then we have a fake map that we've randomly permuted the values about. We're going to generate a lot of fake maps. 10,000, 100,000, depends how much we want to do. And for each one of those, we have the split of the counts, the joint counts into those three groups. And we're going to develop our reference distribution to assess whether our map is random, believable that it came from a random process or not. And that's why we need to set the random seed number so you all get the same result as I'm going to get. Meaning we can reproduce this and we would get the same results. If you don't set the seed number, you rerun it, you'll get slightly different results. Okay? Then we call the joint counts module from PyCell and the joint counts class. And we pass in our binary variable, which is black or white. That's a vector of 44 values. Some of them are 1, some of them are 0. And our weights object, which we've standardized to be binary. And that does the joint counts for us. And it creates an object that has the attributes with the counts. So there were 44 joins that were black-black joins on our map. 44 cases where a shared edge was on the right and the left was both black polygons. There were 43 white-white joins and 32 black-white or white-black joins. Those exhaust all the joins. How many joins are there? Our weights object, WQ, has an attribute called .S0, the number 0. That's counting up all the ones in the matrix and divided by 2, because it's a binary symmetric matrix. So if A and B are neighbors, B and A are neighbors. But that's one join. So we cut it in half. And this tells us we've counted the joins correctly. We know they're split. We know that we had 44 black-black joins. And the question becomes, OK, great. Is that higher or lower than what we would expect from a random process? Meaning for each polygon, we flip a coin. If it's heads, it's the color of black. Move on to the next polygon, flip a coin. Each time we do that, the process doesn't care where that polygon is geometrically speaking or spatially speaking. For our fake maps, the one that used the spatial permutations, this coin flipping analog, right? We did, I think, 1,999 fake maps when we call this method here. The default is to do 999 fake maps that simulate that coin flipping process. The mean of the black-black count was 28 under the null, because you're simulating the null, that the map came from a random process. Okay, so we know what we got is higher. The question is, how much higher? So we use Seaborn to extract the distribution of the black-black counts from all the fake maps, all the synthetic maps, all the maps based from the random permutations. Right, so we collect the BB counts. This is their density. That's the average. This is what we actually got on our map, the observed map. We had 44 black-black joins. And from this, we can develop a pseudo p-value. It's the area of the curve under that density to the right of the red line. And it's like a p-value, even though these are falling out of fashion. So the p-value, it's an attribute that PyCell does for us, but conceptually it's integrating that curve, loosely speaking, and getting the area to the right of the red line. And it's under 1%, right? So it's 0.002. So if you use conventional 5%, this would be significant. Okay? So what we got is very extreme if we're to believe it came from a random process. Okay, so we would reject the null that the process that generated our data is a random one. We could be wrong because we don't know what the true process is. We wouldn't be here if we knew that, right? But we do know that if it was a random process, getting such a result as the one we got is very unlikely. How unlikely? 2 in 1,000. Okay? So that's the logic of the join counts. Right? We count up the joins, And for each join, we say, is it black, black, white, white, or black, white? Okay, how many different maps could we generate this way? Thought experiment. So the way the permutation works is we have a vector of 44 values. The first 22 happen to be ones. Right? A permutation is sorting the indices randomly. So what became 1 moves to position 23. What was 44 moves to 2. And the number of permutations you can do is n factorial. N's 44. N factorial is a really big number, right? So we don't do all n factorial permutations, we sample from them. But that's intuitively what's happening. I think N44 factorial, I know 48 factorial, we could not enumerate all those. There's not enough time in the heat death of the universe to do that. So we sample instead. Okay, so that's for the binary case. We threw away a lot of information just to get this notion of what do we mean by high and low? There's other measures that deal with the continuous data. So we go back to our original variable, median price. We're not going to truncate it to high or low. Now we're using the actual listing prices. And here we're going to transform our weights to be R, which means row standardized. That takes the row sum of the binary matrix, which tells us how many neighbors each unit has, and then it divides the original values by that sum. So if you had 4 neighbors, each of their weights would now be 0.25. They get equal weight. If you had 5 neighbors, their weights would be 0.2. If you had 1 neighbor, it would get 1. That's what the R means for row standardized. And that lets us get the spatial lag as the weighted average. If we kept the weights binary, it would be the sum of the prices in the neighborhood, in the neighbors. And we want the weighted average. That's what the transform does. The test for the global case, the test for the continuous case, where we don't have a binary attribute, but now we have a continuous attribute, is called Moran's I. And it has a very similar call structure. You pass in your attribute Y and your weights object, WQ. We set the random seed again because it's going to rely on the same way to generate the null distribution. Permute the values over the map. So pick up the 44 floats and randomly assign them to polygons. Randomly, because you're playing God in the housing market. You're creating a random housing market. And that's our benchmark. Do that a lot. Calculate your statistic for each one of those maps. Take your original statistic from the real map and compare it to this distribution, just like we did for the joint count. So for Moran's I, the statistic is called I, so it's capital I. We get a value of 0.5957. What is that? Well, now it's not counting joins. It's loosely speaking thinking about the correlation between the value of the median price in a neighborhood and the average median price in the surrounding neighborhoods, the correlation of those two variables. But we can interpret it using the same logic that we did with the joint count. So this is the distribution of Moran's I under the null based on the permutations. Right? So you get something a little bit under 0, and that's true. It's not the expected value of this statistic under the null is not 0, even though if you think about it as a correlation, you might want to think of it as 0, but it's not. It's -1 over n minus 1, where n's the number of polygons. So it gets close to 0, but it's always negative. So that's what we get on average. This is what we got for our statistic. Way, way out in the tail. Right? In fact, none of the 999 fake maps generated a value as high as we saw with the original data. And because we kept more information in the continuous variable, we see a more extreme result. Its p-value is smaller. So again, we would reject the null that whatever generated the housing map, price map, is characterized by a random process. Right? Why? Well, the probability of getting such a result is less than 1 in 1,000. Right? So those are global tests. They tell us something about these maps as a whole. Either that one for the joint count or this one for the continuous case where we use Moran's eye. So in both cases, we reject the null and conclude there's something going on in these housing markets. Prices are not random in space. Questions on that? All right. So why does it matter? You might be asking that we rejected the null. Why do you care about spatial autocorrelation? Why do you think you might care about spatial autocorrelation?
In this case, it could show inequality, things people care about. Someone could just say, oh, it's just random. There's nothing going on here. So it's exploratory. It lets you like dig deeper and find, maybe you can now find like ways to explore causality.
Okay, so these are exactly exploratory methods. The ESDA module is exploratory. They're not developing causal frameworks, but they're uncovering patterns that perhaps we weren't aware of that lead to those kinds of questions. Well, why is this not random? Or why does this appear not to be random? Right? That's what they're designed to do. The other purpose for doing autocorrelation analysis is when you get to the confirmatory modeling part, which we're not covering today. Let's say you were going to estimate hedonic models for housing prices. If the data is spatially autocorrelated, you just cannot use traditional methods. Your inferences are likely to be wrong. So you want to know if the data is spatially dependent so that you can use the right methods. So for two reasons, pattern detection and then diagnostics to whether your assumptions for, say, classical regression modeling are going to be met or not.
Is it possible to have a multi-attribute approach to this? So for example, if price wasn't the only attribute I'm looking at, but I'm generating multiple like spatial autocorrelation maps for different attributes, and then I want to combine them to see importance of one over other.
Yeah. Do you want to say a little bit about the?
Yeah, there's a whole family of new statistics that are coming up around this problem. Some of them involve like measurement of like a spatially weighted Mahalanobis distance. There's a whole bunch of combination spatial feature kernel stuff.
Okay.
That's kind of the frontier of literature right now. So yeah, some of that's implemented in Python, some of it's not available yet anywhere.
And is there a difference if we don't do the Vernoni polygons or Hessian polygons initially, but instead what we do is just do contiguity and then apply, for example, an attribute to look at features like what is the eigenvalue centrality for connected points, like basically doing network analysis after doing the, and would the results be different then?
Different measures of centrality, graph structure, will disagree with different measures of spatial statistical relationships.
Right.
So it can be the case that if you choose a Voronoi polygon representation, eigenvector centrality, the node, is not the same as its local statistics score.
Okay.
Other questions? Okay, so the Moran's eye and the joint count were for the global test. Is the map random or not? These local measures, local statistics, are spatially explicit in that they're going to allow us to detect if there are so-called hotspots or cold spots or outliers. Is the clustering continuous, or is the clustering stationary in the process? If we found for the global map that we reject, or the global test, we reject the null, is it the same process everywhere, or is the process unstable? Or if it is stable, are there certain locations on the map that are driving the overall result? Right? These are some of the applications of what are known as the local methods. So we're going to use the same data, same weight structure, queen. We make our lag price, and we're going to motivate this idea of local stats. Make this a little smaller. All right, so what we're doing here is plotting two variables. On the x-axis, it's the median price for each of the neighborhoods. Okay. The vertical line is the median of the mean. It's the mean. So that's the mean of the medians. The y-axis is our friend, the spatial lag. Right, so for each neighborhood, we know who its neighbors are. We take the weighted average of the medians in those neighbors, and that gives us the coordinate for this axis. This horizontal line is the average of the spatial lag. So with the cross between the two averages, we have 4 quadrants. Okay, quadrant 1 up here. What can we say about that neighborhood? Is it high or low, its price? This guy right here. So its price is about $250 a night. Is that high or low relative to this data set? It's high because it's to the right of this guy, right? So that's a high neighborhood. How about its neighbor? Its neighbors. The value for the spatial lag, the average housing price in the neighborhoods that neighbor that neighborhood, is that value high or low? It's high. It's above the horizontal line. So if you're in quadrant 1, you are a market that has high median price, and your neighbors are also high-value neighborhoods. Right? That's what's going on in this quadrant. Quadrant 2, what do we have? Say this guy, that neighborhood. Is it high or low, the median price? It's low, but what about its neighbors? They're all high. Right, so this is a relatively low-priced neighborhood surrounded by higher-priced neighborhoods. Not higher than it, but higher than average. Okay? So this is low next to high, where the first one is the focal unit. So here we had high, high, high focal, high lag. Here we have low focal, high lag. Quadrant 3. If you're in quadrant 3, what does that tell us? Low focal, low in the neighborhood, of the neighborhood. Okay? And then finally, quadrant 4. What are these guys? High price, surrounded by low price neighborhoods. Okay? So this is called a Moran scatter plot. Moran, same Moran as Moran's eye. But this division between the 4 quadrants gives us the ability to define the type of local spatial association across these 4 cases. So in quadrant 1, you have positive spatial association of a high type. This value is high, and so is the value in the neighborhood of that neighborhood. So this is high positive spatial association. This is also positive spatial association. You have value similarity, low values, but also spatial similarity, because these are neighbors. Right? That's positive association, but it's of a different type. So you might think of this as a poverty cluster, so to speak, a wealth cluster. So on the diagonal, you have positive spatial association. If you know something about the price in this market and the data is positively spatial associated, that tells you about the prices in the context around that neighborhood. Or if you know the context around a neighborhood, it tells you something about what you should expect to find in the focal neighborhood. Okay? These got
data points under the diagonal, the first quadrant. So there is like a high price and
these guys in this up here.
One about 300 plus.
This guy.
Yeah.
Yeah.
So there is abnormally high with a low focal.
This is a high. The price for the focal unit's 300 and whatever, and the average in the neighborhood is under 200. So if you're below the diagonal, it means the focal units, and you're up here, is higher than what's going on in the neighborhood. So quadrants 1 and 3 are positive spatial autocorrelation, but from a local perspective. Value similarity and spatial similarity. Quadrants 2 and 4 are known as spatial outliers, because you have value dissimilarity with spatial similarity. right? The neighbors are spatially similar. That's our definition of spatial similarity, whether you're a neighbor or not. But here you have high value surrounded by low values. Here you have low value surrounded by high values. Okay? So we have these 4 cases. These are high, are so-called hot spots. Hot meaning high for the attribute you're measuring. We're looking at housing prices, but it could be crime rates, it could be disease rates, it could be car accidents. High for the attribute. High. These are low, or cold spots. Low values next to low values. These 2 other cases are spatial outliers. And we have 2 of them. I like to call this one where we have low surrounded by high, like the donut. You have a donut with a hole in the middle, not a jelly donut, but so empty in the core, and the periphery is where all the action is with regard to the attribute. And down here, you have a diamond in the rough. You have high value in the core, not much going on in the periphery. Okay? So this direction are outliers. This direction is positive association, spatial association. This red line, the slope of this red line, is the value of the global Moran's eye statistic that we saw already. Right, so if there was no spatial association on our map, our original map, we would expect to have the dots spherically distributed into the 4 quadrants, because there would be no association between the housing value in the focal unit and what goes on in the neighborhood. That's intuitively what randomness is about. But this is clearly not a zero slope line. All right, so to calculate these local statistics, there's actually a lot more that has to happen. Number 1 is statistics, plural. We no longer have one statistic for the entire map. We're going to calculate a measure for each location. And that's why they're called local. The signature is the same, though. We call Moran.Moran_local instead of Moran. Pass in your y vector and your w object. And that creates a local I object that has a bunch of attributes. Number 1 is Q. Which quadrant are you in? So these are numbers between 1 and 4, right? 1 is this quadrant, 2 is that one, 3 and 4. So observation 1 was in quadrant 4. Observation 43, Python 0 offset, was in quadrant 1. Okay? Also, what goes under the hood here are the permutations. Just like we did for the global test, we need a reference distribution to decide if our statistics are extreme relative to our maintained null. However, here, instead of 999 permutations for the one global statistic, we have to do that for each polygon. Right? We have to do that for each polygon. So this is a lot more computationally intensive. And the reason you have to do that is so that you don't include yourself as your own neighbor, loosely speaking. We get a p-value, p-sim, for each observation. Each observation gets a value for the local I statistic, and then we need to decide whether it's significant or not. And therefore, we use those distributions just like we did for the global stat, but instead of one reference distribution for all values, we have a different distribution for each location. But the interpretation is the same. Where is my observed statistic in this reference distribution? So we could plot 44 densities, but we're not going to. We're asking how many of our local statistics had p-values below 0.05. Right? So there's 18 of our 44 statistics that are significant by this criterion. Okay, so we want to find out, okay, great, where are they, what are they? First, the hot spots. So those are the ones that are in quadrant 1 and are significant. Not just being in quadrant 1, but also being statistically significant, being more extreme than you're comfortable with under the null. So those are the high value neighborhoods that are co-located with other high value neighborhoods. It's not enough just to be a high value neighborhood. You have to be contiguous to other high-value neighborhoods. Right, so that's our hotspot map, cold spot map. These are the ones in quadrant 3 that are significant. So blue for cold, in different part of the city. The donuts, which is quadrant 2, hole in the middle, right? So this is a relatively low priced housing market surrounded by high housing price markets, right? So that's our donut, one of the outliers. And then the diamonds, these are high value neighborhoods that had high median price surrounded by neighborhoods that had low median price and significant. So putting them all together, we're only plotting the significant ones. And we have those 4 quadrants. Right? Red is the hot spot, high, high, quadrant 1. The gray is not significant, so we put those on so we see them anyway. The blue is the cold spots, quadrant 3. The donut up here, and the diamond down here. Okay? So if you're an investor, where do you want to buy property?
The donut,
Yeah.
second quadrant,
Why?
it's priced,
Right? If there's diffusion, if the growth is going that way, that market might trip sooner than, yeah. You could use it for those purposes, yeah. Okay, so those are the local statistics. They identify the interesting locations, whether they're strongly emphasizing the global pattern, which certainly this one and this one are. Those are in quadrants 1 and 3. Similarity in space, similarity in value, high next to high or low next to low. But then less prevalent, but still there, are the outliers. Okay? Questions on the autocorrelation? All right. Before we leave the autocorrelation, these are all static. This is a cross-sectional analysis. We have the data for one time period, right? So this notion about, well, if there's diffusion and the growth cluster expands, then we probably want to invest here. But that's making a guess about the dynamics of the process. And one of the ways these statistics are used is if you have panel data, if we had the Airbnb data for multiple time steps, then one can have a time series of these scatter plots, one for last year or the year before, and you're interested in the movements across these quadrants. So we have packages inside PyCell that deal with those kinds of questions as well. All right. Last notebook, and then maybe we'll have time to do the exercise. Has to do with notions of clustering and regions. So region building and clustering. Clustering in the terms of multivariate clustering. You have a multivariate data set, say US Census data. You have, or for our case, our data. We have the Airbnb data. For each listing, there are multiple attributes. Yeah, the sales price, how many people, and other attributes. What we'd like to do is cluster together the listings that are similar to other listings in attribute space. Okay, that's a multivariate clustering problem. But we also, since our focus is on spatial data science, we'd like to incorporate geography into that clustering process as well. And introduce this notion of marrying, if you will, spatial similarity and attribute similarity, and define clusters from that perspective. Okay, so that's what we're going to do with this notebook. We read in our neighborhoods and the listings, plot them, We constructed some new information. Levi calculated median price per head. So in the attribute data, you had the listing price as well as how many does it accommodate. So on the right, that's the ratio of those two. Price divided into how many people can live there. I'm not staying at that 12,000 place. I would invite people if I was, but it wasn't. So we're going to start with traditional clustering with scikit-learn. It has many clustering methods that you could use. We're going to apply that to our neighborhoods data as well as the point data. We're going to look at two clustering methods, k-means. People are familiar with k-means clustering? Or no? How many never heard of it? We'll spend some time on it. Okay, so k-means clustering is about, we have a set of objects, and we want to assign them to groups, i.e. clusters, such that everybody is assigned to one and only one cluster. Right? And we've clustered everybody. So mutually exclusive and exhaustive. How do we do that? Well, we could take the IDs and sort them and say the first 5 are in cluster 1, next 5 are in cluster 2, and so on. Yeah, that would make them mutually exclusive and exhaustive, but in terms of similarity, it's probably random noise. So these clustering algorithms use the distance in similarity in attribute space. So how similar are the prices? How similar are the sizes? Whatever attributes we can get in the data, and we develop multidimensional similarity indices. And then we group together more similar listings into those mutually exclusive and exhaustive partitionings. Okay? So k-means works by, you have, we're doing it for the neighborhoods first. We have 44 neighborhoods. And I want to form 5 clusters of the neighborhoods. So I create a model called k-means, that's from scikit-learn, and I tell it I want 5 clusters. What this is going to do is take those 44 neighborhoods and put them in the 5 buckets. Right? Those are our clusters. How does it do it? It depends on the options, but you start with you randomly pick one of the neighborhoods, or you pick 5 of the random seeds. And then you look for each of the unassigned neighborhoods, which of those seeds is it closest to. Right, so I first pick 5 random neighborhoods. Those are the seeds for the 5 neighborhoods. Then I have 39 unassigned neighborhoods. I loop over those. I pick the first unassigned neighborhood, and I see which of the 5 seeds is it closest to in attribute space. And I attach it to that seed. And I do that for the other unassigned ones, and I currently have a feasible solution. I have 5 clusters, everybody's been assigned, but then I re-establish the center of the clusters by taking a multidimensional average of the ones that have been assigned to that. And then I step through the list again, I say, should I move this guy to a new cluster? And I keep doing that reassignment process until it converges. Okay? That's what k-means does. It gives us labels. So we create a model, then we're going to fit the model on our neighborhoods data with our clustering variables. And our clustering variables, we're going to use can't remember what we were using. I skipped over it. Well, let's see what they are. Oh, we're just using median price. So we're faking multivariate clustering. We're just using the median price. The result of fitting the k-means model is it gives us a k-means object. One of its attributes are the labels underscore. These are the clusters that each neighborhood was assigned to. Right? So the first neighborhoods is in cluster ID 2. Last neighbor is in cluster ID 1. We're going to attach those labels as a new attribute and then plot it. So that's k-means from scikit-learn on the median prices. So form me 5 clusters based on price similarity, no other attributes. And the color denotes which cluster you belong to. Not necessarily if it's a higher or lower value, but membership in a group. Okay? So anything interesting about this map?
Even though you're not like explicitly accounting for space in the clustering method, you still see spatial clustering.
Okay, you see, let's say for the green cluster, most of it's up here. You have polygons. Units that were assigned to cluster 1 are co-located. Similarly for cluster 0. Right. So there's some spatial structure there, and this is an aspatial clustering routine. It doesn't explicitly take geography into account, but the spatial distribution of the attributes, when we saw the autocorrelation analysis, is not random, so it's picking that up. Okay? We can get the sizes of the clusters, meaning how many neighborhoods were in each of the 5 clusters. So the cluster number 4 only has 1 polygon, that center one. And then we get the values of the mean of the medians for the housing prices in the 5 clusters. So that cluster that only had 1 neighborhood has the highest value, 335, right? And that's this guy here. Okay, so that's k-means. Next we'll do agglomerative clustering. Agglomerative clustering works by, we start with 44 clusters. Everybody's in their own cluster, but that's not useful because there's no summarization of the data. Then we search for the closest pair of listings, closest pair of neighborhoods based on multi-dimensional space, but here we're just using price. So we find the 2 neighborhoods that have the smallest difference, and they form the first cluster, the first real non-singleton cluster. So after step 1, we have 43 clusters. One that has 42 singletons, and this one cluster that has 2. Okay? Then we keep going. We find the next, we treat this as a single thing. We collapse it. We have 2 neighborhoods that form that cluster, but we take their average and treat it as its 1 unit. And then we search for the closest pair again. And it could join one with that one, or it could join 2 other ones. And we keep going until we have 1 cluster that contains everything. And this gives us something that looks like this. If the wireless gods will. This is a dendrogram, right? So step 1 would have clustered neighborhood 2 and 10. Step 0, we have all the neighborhoods not clustered. And then you keep going until you join singletons to clusters or clusters to clusters, until you're at the top of the tree where you have 1 cluster. Everybody's in the same cluster. That's what agglomerative clustering does. Agglomerate and move up. And how you measure similarity has to do with the linkage option. Words is the distance measure. Once we're done, we have the same properties of the object. We have the labels. And we can introspect that and get how big are the clusters, meaning how many neighborhoods are in each of the clusters. And we see some similarity. That 4th cluster falls out again, the singleton, by itself. And we can plot that as well. Okay, we said we wanted 5 clusters for agglomerative, and what that does, if we go back to our dendrogram, it tells us where we're going to cut the string horizontally, so that when we cut it, we have 5 clusters of bundled neighborhoods together, right? If we cut it here, that would give us 2 clusters split here, right? If we cut it here, we'd have, well, I'm not going to try and count. So when you say K is 5, it finds out at which horizontal cut would you get 5 clusters. That intuitively, that's what is happening. All right, again, see spatial structure, non-randomness, and the co-location of the the membership in the clusters is not random in space. Whoops, I don't want to do that. And then we can compare the two clusters. So k-means on the left,
I think they're flipped.
they could be. We mislabel them.
Yeah.
Okay. Okay, so the geography is a result of these clustering processes, but it's not explicitly built into the clustering processes. There could be reasons where you want to respect some spatial considerations in forming the clusters and not rely on the data to allow it to emerge in the solution. One of the reasons you want that is if you're thinking about neighborhoods, for example, like socioeconomic neighborhoods. You are either inside your neighborhood or you're not. You don't leave your neighborhood to get to your neighborhood. So if these were neighborhoods, these clusters or neighborhoods, cluster 1 is here and here. It's spatially fragmented. And that's not a socioeconomic neighborhood, right? You wouldn't say, I live in this neighborhood, but my neighborhood also is over there. You're either inside the boundaries for your neighborhood or you're not. All right? So we could say, well, we want to form clusters that are not spatially fragmented for those kinds of problems, those kinds of applications. You may be running a business where you need to assign people in the field to service regions. And you don't want these regions to be fragmented. It's inefficient from like an optimization type approach. So we want to build those constraints into the clustering solution. And fortunately, we can do that leveraging the really nice architecture in SciPy, and scikit-learn rather, by passing in a PySal sparse, the queen weight that we've been using. We use its sparse attribute here, and we pass it into the agglomerative model as a connectivity, the value for the connectivity option. And what that does is it repeats the clustering, but it only forms clusters such that we're going to have members being spatial neighbors. Right? So we didn't have to reinvent the wheel here, although we have on separate packages. This is really, really nice, and it speaks to the strength of the SciPy ecosystem. This is one instance where this kind of thing happens a lot. You discover this other library that does exactly what you want to do, and we have a data structure that fits really nicely in there. So let's do this with Ward. Agglomerative clustering, we want 5 clusters, but now you see what we mean by there's no fragmented clusters. The blue one is not split such that if you had the connectivity graph, it would have 2 components. It's a single connected component, right? As are the brown ones and the green ones. All right, so if you need to respect this type of constraint, you can do it fairly straightforward option. Does that make sense? Okay, and then we can do the same thing on the points. We've been going between changes of support, working with points, then switching to polygons. We're going to go back to points here. And we're going to make use of things we've already seen. We did the Thiessen polygons a couple of notebooks ago, and we stored it to disk, hopefully not in 3,000 files on someone's hard drive. Or 11,000, sorry. We're going to read that clip Thiessen's geopackage, which are a bunch of polygons, and PySal we call queen from data frame. So it takes that data frame and says, give me the queen neighbor relationships from that Voronoi polygon, Thiessen polygon. Same, the names are different, but it's the same thing. So now we have our queen contiguity structure for our 11,000 points. We take the log of the prices because agglomerative clustering, what was the rationale? Does poorly on price data is not normally distributed. So we do a log transform on it. And then we do agglomerative clustering with the spatial constraint, just like we did before on the polygons, but now we're doing the clustering on the points with the Voronoi neighbors as our weights object. And it runs pretty quickly. We'll plot it. So now the color is denoting what region was that point assigned to. We don't see the Voronoi polygons, but they were under the hood expressing the contiguity constraint. Okay? And just like the polygons, we can query the clusters, the regions, and ask how many points are in each of the point clusters or point regions. Now there's quite a bit. We had 11,000 points to cluster. And we can do it with agglomerative as well. And then plot the different clusters individually, where they are in lat long space. Okay? Questions on the clustering and region building? How you doing for time? Okay, so do you want to do the last problem set or ask questions about anything else?
Yeah, just a general question. So how do you get the data? Is it Zillow or Airbnb? So it's a public data or how it
The Airbnb data, you scraped it?
It's on inside Airbnb. It's a provider that focuses on providing extracts of various metro areas. Comes sometimes in like a time series form, sometimes in an open form, but that's how that was accessed. I'm not sure if it does. I use the inside Airbnb extracts because do some preliminary cleaning and deduplication of screens. So,
It used to have API, but they canceled. They're no longer accepting applications.
yeah.
Oh, yeah?
So the spatial clustering, is there any other context we can use it? Have you seen any, like right now I'm in cybersecurity, so where the attacks come from different IP addresses from, say, like Russia or somewhere, and we can locate the IP address as well as the latitude and longitude. And based on that, like we could come up with similar clustering. Like if some of the IP address located in different countries and they're accessing certain website like where we care of,
Mm-hmm.
and then we can try to make a spatial clustering like where more hits came from, which location.
Yeah.
And I think this is a really great like to explore in that context of cybersecurity and network security and
Mhm.
all that.
Yeah, that would be a great use case. Clustering gets used for many, many domains, for sure. Okay, do you want to work on exercise or learn other stuff about PySal or just give you overviews of what's in the library, stuff we didn't cover, and point you to resources?
Is it possible to do Shannon's entropy, spatial Shannon's entropy in Python?
It will be, yeah, it is. So the project itself has, it's a federation of packages. So if you go to pysal.org, that's the public face to it. There are packages, we covered today libpysal, some ESDA, map classify. I think those are the ones we hit. But there's many others. There's a new one called segregation that has a bunch of indices along the lines you're talking about that just came out. It's used for segregation analysis, but you could use it for other purposes as well. So the way the library is installed, if you want all these things, you install the meta package, conda install PySal or pip install PySal, and it'll get everything. We have these PySal lib, as well as ESDA. Gitty is for space-time analysis. Inequality is for inequality analysis. Point patterns, which we didn't cover today, really. There's a module to do that. Segregation. Spaghetti is for point patterns on networks. So if you had phenomena that are constrained to a network and you want to do spatial analysis on it, that's what spaghetti does. And region is in limbo. It's probably going to go away and get reinvented, but that's the regionalization, the stuff we ended with, forming compact regions. Then there's a modeling layer, which we didn't cover today. This would be for the confirmatory type modeling, spatial econometrics, spatial general linear models, spatial interaction models, where you're trying to predict migration flows or different types of interactions between origins and destinations. And it's a model, that's why I put it in the model layer. And varying component models that Levi heads up. We all work together on these different packages. There's a bunch of us on the team. The visualization, we saw a little bit of Map Classify today. There's a package called splot that Stephanie Lemnitz, who's here, giving a talk tomorrow, developed. Legendgram is a cool visualization for the legends. And then there's a notebook project that we're working on, so you could run all this stuff locally before you use it.
So what is rasters, the other?
So the rasters, when PySal started, it was in the vector space, because that's most of us at the time worked in social sciences, and the dominant spatial data structures are vector data, so polygons, points, and lines. The raster stuff was more in the geophysical realm, so hydrology, ecology, that kind of stuff. And so our research interests weren't there, so we focused most of PySal up until very recently. So this stuff we didn't cover today, although you have the notebooks. There was the set on rasters. Levi's been working more with rasters lately than I have, so I don't want to misspeak about it. But we've never had raster support inside PySal because there's other really good libraries that have it. Is that a fair thing to say?
So overall, the problem set and the solutions are there, right?
Yeah.
The problem set is more like experimenting with different libraries and packages and come up with some visualization.
Yeah, so the problem sets are here at the level. And then the solutions are also notebooks that are fully worked out. So you have them.
Do any of the PySal components require online access, or can the package be used completely offline?
I think, well, Contextually is not part of PySal. That's the one where you have to hit the tiling service. I don't think any of them do. Yeah.
They're all able to be used offline.
Yeah. Yeah, one of the motivations we just refactored the library, so now if you don't want everything, you can install the specific packages you want, so it'd be lightweight. And one of the reasons for doing that is we have partners who work in Census on site, and they have really strict requirements as to what they can install. So they couldn't install everything. They wanted a la carte kind of stuff. And I think it cannot go out off-site, so it has to be local. Any other questions? Well, we could stop there. Oh, yeah.
Sorry.
No, that's fine.
Have you found any cool exploration projects using your guys' library yet?
What kind?
Kind of exploratory projects that people have used with PySal yet? Aside from your guys' own internal work?
Uh-huh.
Like any contributors?
Yeah, there's people, well, this morning at the breakfast, I sat next to a guy who works for a large multinational petroleum company that I won't name that uses PySal. He wouldn't tell me for what much, but
Maybe in oil spill or something?
I don't know. Now, we both worked with companies before that use a lot of PySal and related tools for all kinds of research. And it was born out of our own research needs, for sure. But a lot of people are using it. Yeah. So if there's stuff that we didn't cover that's not in the library you want, let us know. It's a really friendly group. People can get involved. And maybe we'll stop there. All right.